Now we're live on YouTube too. That's okay. 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 Welcome everyone to the ICMAM Latin America Satellite Conference on Differential Geometry. It is a pleasure to open this virtual space dedicated to sharing recent advances, open problems, and new directions across the landscape of differential geometry. Thank you for joining us from so many places. Let me begin by situating this event within the ICMAM Latin America initiative. ICMAM stands for an international community of mathematicians from Latin America. Since its origin in 2020, ICMAM Latin America has worked to advance mathematical research in Latin America and the Caribbean, increase the visibility of our region's work, and promote collaboration among mathematicians within and beyond Latin America. Our mission rests in three pillars: building a strong mathematical community by connecting young researchers with experts, amplifying and giving visibility to the work of women mathematicians, and leaving a legacy through publications. Today's conference is part of ICMAM Latin America's ecosystem of satellite conferences. These conferences expand the reach of the main ICMAM conference by offering thematic spaces throughout the year. In addition to this meeting, the satellite program has included initiatives in analysis and PDE, data science and machine learning, algebra, combinatorics and number theory, and pseudo-differential operators. You can see the records of these conferences on the ICMAM Latin America website. The most important part of any scientific meeting is its speakers and participants. This year, we are pleased to host a distinguished group of invited speakers, namely Professors Ana Meneses, Ana Fino, Francesca Orionzo, Jason Lotay, Jorge Lauret, Lino Grama, Mariel Saez, Megan Kerr, Nicoletta Tardini, and Ryuichi Fukuoka. We are grateful to them for accepting our invitation and contributing to this conference. Our sincere thanks also go to our scientific committee members, Professors Alexandre Santana, Asia Mainenti, Enrique Lopez, Kenerson Lima, Leonardo Cabenagui, María Lenice Hernández, Sandra Carolina García, Viviana del Barco, and Vladimiro Benedetti. I also want to personally thank Juliet Saavedra, co-organizer of this event, Duan Cardona, Scientific Director of ICMAM Latin America, and Karina Navarro González, President of ICMAM Latin America. To end these acknowledgements, I want to highlight the support of the Universidad de las Américas in Ecuador and the Universidade Estadual de Maringá in Brazil, and to express our thanks to the Asociación de Matemáticos del Salvador for their institutional support, especially to Professor Joseman Rivas. ICMAM Latin America is, above all, a community building project. Beyond conferences like this one, ICMAM cultivates networks for early career researchers, promotes regional cooperation, highlights the work of women mathematicians, and supports diffusion channels that disseminate the work from Latin America to the world. We invite you to consult the schedule and abstracts pages on the conference website to plan your attendance. Over the next 2 days, we encourage you to participate actively. A space for questions and answers will be available at the end of each talk, and a few practical notes for a smooth experience. Please double check the time zone alignment with your local time so you don't miss sessions of interest, and keep the Zoom details handy. The website will remain your central hub for updates, program changes, and any materials that speakers choose to share. Above all, remember that an online conference succeeds when the chat is lively, questions are generous, and we make a space for contributions from junior and senior participants alike. If you are new to ICMAM Latin America, we encourage you to learn more about our programs and consider joining this community. Thank you for being here. We wish you an inspiring conference. And with that, it is my pleasure to pass it over to Dr. Luan Cardona, who is the Scientific Director of ICMAM Latin America. Please, Luan.
Okay, thank you very much, Professor Brian Grajales. So today there are participants, ICMAM Latin America, the international community of mathematicians from Latin America, takes action in the development of the mathematical research in differential geometry in Latin America. Just as a remark, I would like to bring to our memory that it was probably in the first methods and proofs of Euclidean geometry, developed more than 2,000 years ago, that several of us found interest in pursuing a career as mathematicians. From ancient times, geometry, in its axiomatic presentation, has given us intuition of the plane and of the space, and from a modern perspective provide us fundamental notions in mathematics, as the one of manifolds and of vector bundles. Famously, Eratosthenes calculated the circumference of the Earth around 200 years before Christ, and also the Riemannian geometry was used in the 20th century in the development of the general relativity theory of Einstein, showing us the power of the methods of this discipline. Today, we know that differential geometry was constructed, among other things, by contributions of big names in the history of mathematics: Euler, Lagrange, Gauss, Riemann, and in more recent times, Beltrami, Klein, Christoffel, Sophus-Lee, and Hamilton. Our generation can testify also of beautiful developments in these disciplines. In the 1960s, with the proof of the Atiyah-Singer index theorem, for example, leaving us mathematicians that have changed our perspective in the fields, as Michael Atiyah, who got the Fields Medal and the Abel Prize, and Isadore Singer, who got in 2004 the Abel Prize. We also remember Grigory Perelman and his proof of the Poincare conjecture. The mathematical activity of several researchers from our region, as Luis San Martin, for instance, former editor of the Journal of Lie Theory, and Fernando Coda Marquez from Princeton University, current editor of the Journal of Differential Geometry, shows us that there is an enormous potential in promoting this idea in our region for the development of mathematical research in Latin America. It is thanks to this goal, the one of promoting mathematical research in differential geometry, that Brian Grajales, a Colombian mathematician, vice president and former president of ICMAM Latin America, has started the organization of this conference series. The list of speakers of the ICMAM Latin America Satellite Conference on Differential Geometry 2025 is impressive. All these names were attracted thanks to the big effort of the organizers, to leading young mathematicians of the new generation of researchers in differential geometry, Brian Grajales, the founder of this conference, and also Juliet Saavedra, a very promising young mathematician. It is really impressive to see the quality of research carried out by these two mathematicians. Throughout their early contributions to differential geometry, Springer, Birhauser, have offered them to start a new book series, which will be associated with versions of this conference now and in the future, and will be dedicated to collect contributions of established researchers in differential geometry from Latin America to provide a perspective of the current state of the art of this field in our region. So, from the organizers, you will receive the invitation to support this initiative soon. In my role as scientific director of ICMAM Latin America, I just would like to invite everyone to follow these talks and to promote discussions that could lead to future research collaboration. So thank you very much. I pass the voice to the chair.
Thank you, Duban, for that words. Okay, the Professor Kerr, we will start in about 15 minutes, but maybe we can check if you can share your screen or
Yeah,
everything is working well.
Okay.
So let me stop my sharing here.
All right, to see if I can make it work. Oops, I just want to share. Oh, I know. I can see that I am also we don't want any of those. Zoom. Oh, hold on. I know. Okay. This is in some corner, right? Here we go. Just good. Screen mirroring. Here we go.
I was sharing,
Here.
maybe
know.
you can share now.
We see my, hold on, okay. And then, oh yeah, okay. Oops, how do we make that? There, okay. Okay, there it is, right? Do you see the talk?
Not yet.
Oh,
Mm,
not on Zoom. Okay. Oh, wait, oh, I see, wait a minute. Just going on. All right. Screens, oh, advanced, where's the iPad? Oh, here we go. Now,
Okay, I think.
screen mirror, I know, I thought I did that.
Okay, I started to look at that.
Yeah, sorry, it's spinning
It
beach ball.
says it
Okay,
says that you start screen sharing, but I cannot see
oh, and not now?
slides or anything.
Ooh, what's going
Maybe
on? I see you don't see it.
no. Maybe the participants can
Oh, I see.
give
But I
some
don't
feedback.
actually, okay, all right. I don't really need to do this on my iPad, do I? No. Okay, let's see. Let's do this. And now, let me just stop sharing and try this again. All right. Just the computer screens. Here?
Now it's working.
Okay.
Okay. Existing criteria for compact homogeneous. Perfect.
Okay. All right, and then let's see if we can do this in full screen mode.
Okay. Maybe you can try to pass the slides.
Yeah.
Oh, it's
Well,
perfect.
that will work. Okay. Is there something cleaner? Yeah. Okay. All right. Are you looking at like, also like the people watching? What do you see just the tech? Oh yeah, the tech window? Yeah. Okay.
Yes, it is.
Yeah. Okay, good. All right. All right, so
Okay.
that's there. Okay.
So I think we
Yeah.
can
Take
wait for
12
a few
minutes.
minutes and then we will start.
Good. Oh, it's 7:30 in the morning for you?
No, I am Brazil, so it's
Oh yeah,
9:20.
yeah. Okay. Yeah,
It's
yeah,
7:20 in Colombia.
yeah, that's right.
Yeah, but I think this time works for everyone. We have people from Asia.
Yeah.
East
Yeah, yeah, yeah.
stations.
The time zone part is fun.
Yes, it is.
Yeah. Well, this is great. I really like the Zoom conferences. On the one hand, if you go to a conference, you can concentrate on the conference. On the other hand, yeah, I'm not at a big university, so these these are very nice because there's
No,
not a
okay.
weekly seminar in differential geometry.
Nice. I think
Actually,
that
today we have a speaker coming, but she's going to be talking about it's a talk for undergraduates.
no, I think we learned something from the pandemic, right?
Yeah, that's right.
Because maybe we learned that we have enough technology to connect worldwide. And I think that was a good thing for that.
That's right. I agree. In the same way that I don't really like teaching over Zoom, but I think
Ah,
collaborating is very effective. So, yeah.
not teaching novels. Why
Well,
don't you like?
uh, as you can see, like I'm not that good at the hookup and all that stuff, but I think it's also, I mean, uh, it's, for students, it depends on the students, I think, sort of, but if they
Yeah.
have any time, yeah.
Maybe you get more feedback in person
Yeah,
about the
yeah, yeah,
explanation or something like that.
right.
I agree.
Yeah, yeah.
Maybe it's not good enough for teaching.
I mean, it's better than nothing, but
Now Professor Megan Kerr is familiar with ICMAM Latin America.
yeah, yes, it's wonderful. Yeah.
Yes. Brian is our leading researcher in Brazil about ICMAM. We were very happy that he started this series of conference in differential geometry. It's very active, so we expect that this initiative will attract many researchers in differential geometry from Latin America. So
Yeah, this looks terrific. Yeah. It looks like a breadth of topics, but definitely sometimes I'm eager to hear. Tomorrow morning, I'm teaching basically through till 12:30. So, but today, be good.
probably both of you have a common point in your research, right? Because Brian also works
Mhm.
compat geometry of compact homogeneous
Yes, yeah,
spaces and
yes,
metrics.
yes. It's nice to meet.
Well, some homo professor. I think that I don't know. I made a work about Einstein metrics on real flat manifolds, but ever maybe I want to hear what you are going to talk about. Maybe I have some questions, but I will let them for the end of the talk.
See, yeah, I think there'll be time for questions. I think it's about 45 minutes. So,
And the idea is maybe between 45 and 50 minutes
yeah.
on your talk and 10 minutes for questions. Mm, So
Professor Kerr, you make all your career in the USA, right?
Could you say that again?
Uh, all your career have been done in the
Yes.
USA, right?
Yeah,
In the USA,
exactly.
right?
Yeah, yeah. Yeah.
Interesting.
I was a student of Wolfgang Ziller, who did a lot of work many visits to Brazil. But after I was a graduate student, so my academic siblings often spent a semester at IMPA, but the younger ones. And then I've been to Argentina once for a conference where Jorge Loret was one of the organizers.
Next year, we are going to have our main congress, ICMAM Latin America 2026. You are welcome, of course, but maybe of interest for you, we are going to have talks by Simon Donaldson from Imperial College. Simon Donaldson,
Yeah, yeah.
who is very well known by contributions in the geometry of four manifolds.
Yep, yep.
And many
But,
other mathematicians.
by the way, Juliet cannot be here in the morning, but
Okay,
greetings from her.
okay.
Okay, I think we can start now. Maybe it's 3 minutes before the time, but I think we have enough participants. It is a pleasure for me. It is an honor for me, actually, to introduce you, Professor Megan Kerr. She's going to talk about existence criteria for compact homogeneous Einstein metrics. So welcome, Professor. Again, thank you for supporting this event. And please, you can start whenever you're ready.
Okay, well, thank you very much for the invitation. This is an honor for me and a pleasure, and I welcome questions. So just interrupt me if you have questions. So the work I'm talking about is close to a lot of things I've done, but also is the particular project. Well, is a work in progress, so I'll just share some partial results. But also is work with a working group that came from a Women in Geometry workshop, and the group is Isabel Beach, who's at the University of Toronto, Aide Contreras Pereiro at UNA Morelia, Erin Griffin, who's at Northwestern, and Catherine Searle at Wichita State. And I'm just going to scroll up. Okay, so Einstein metrics are metrics of constant Ricci curvature. I don't look at space-time, so this is a positive signature. So these are metrics of constant Ricci curvature. And this, so we know constant sectional curvature is pretty special, and constant scalar curvature is not so special at all. Constant Ricci curvature is sort of right in the middle. And that is sort of nice. There's only a few topological obstructions, but still, there's plenty of examples, but not like an abundance of examples. And so this is a case where it makes sense to add isometries, and in particular, looking at homogeneous spaces. So we have a simple, compact, well, actually, you don't need to have a simple, just a compact connected, simply connected homogeneous space is what I'm going to be thinking about. I have a compact Lie group acting transitively by isometries. And if you think about the subgroup fixing a point, that's called the isotropy subgroup, and G mod H is, it can be thought of as isometric, isometric to our manifold M. All right. We could decorate H with the point it's fixing, but you get conjugate subgroups from different points. So we don't need that. Well, I won't worry about that. And then the question is, like, what conditions necessary? What do you need in order to guarantee the existence of a G-invariant Einstein metric? So on your homogeneous space. All right. Now, the other thing that is true about Einstein metrics is constant Ricci curvature is that they have a variational characterization. They are critical points of what's called the total scalar curvature functional. So on compact manifolds, if you look at the volume 1 metrics, so that whole moduli space, you can define the total scalar curvature. Total scalar curvature is the integral of the scalar curvature over your manifold. And so the critical points of that functional are exactly the Einstein metrics. All right, and then I can say, so if we're thinking about a compact manifold, then if we want an Einstein metric, the scalar curvature is going to be greater than or equal to 0, and then you'll get 0 Ricci curvature if and only if the metric is flat. All right, I want to look at G-invariant metrics, and it turns out that in the homogeneous case, then we would want to look at G-invariant metrics. One thing to note is that we don't need to integrate anymore because now the metric is, that Lie group is acting transitively by isometries, so we don't need to integrate. So it's really just the scalar curvature, but also we don't lose any data. The G-invariant Einstein metrics are exactly the critical points of that T when we restrict to our G-invariant unit volume metrics. All right. So we still have that variational characterization. All right, so now the other thing that's nice about homogeneous spaces is that you can really think about what is in that moduli space of unit volume G-invariant metrics. All right, and so if you just pin something down, so fix a bi-invariant metric on your Lie algebra, and you just at your favorite metric, that could be the negative of the Killing form, for example. And then I can take the Lie algebra of G and write it as a sum where I have the subalgebra of my isotropy subgroup, right? So H, and then its orthogonal complement. And that orthogonal complement, a vector space inside the Lie algebra, is the tangent space to my homogeneous space. So at a point, say H. All right, but then I have this comparison metric, and I can compare two metrics, right? And every unit volume homogeneous metric on G mod H is basically, I can vary the inner product on that vector space factor P, right? And I can compare it to my comparison metric. So varying is really the same as varying that L, right? So I don't want to annotate, right? So where L is equivariant, at H equivariant, right? It goes from P to P, it's a linear transformation, it's positive definite, and it's symmetric with respect to Q. Undeterminate 1, okay. So the upshot is that we can describe all of our metrics by what they do on each component. I'm going to think about decomposing P into its irreducible modules, right? Summands, all right? And so if we can write P as a sum of K irreducible summands, I'm going to just talk about this. It's simpler if we think about these as being pairwise inequivalent, all right? And then, so in that case, the decomposition is unique. And we have Shor's lemma that says L is this equivariant map. It's an intertwining map. And so it needs to be scalar on each irreducible summand. So we can think about L as having these scalar blocks along the diagonal. And so in particular, the whole sort of, every G invariant metric now is described by these K parameters, right? Where we are rescaling on each of the p sub i's, right? The sum of the p sub i's is our tangent space, and there we can rescale on each piece. All right. So from here now, with those x sub i's, they become, we really can write the scalar curvature in terms of those guys. All right. So there are the x sub i's in here. This formula, because due to Mackenzie Wang and Wolfgang Ziller, I should say, just with this. So this approach is very nice and clean and simple. All right, and in here, there are all these constants. So d sub I is the dimension of the ith summand, and b sub I uses our add invariant, bi invariant q, right, and compares it to the killing form. And then this IJK is a symmetric triple, right? And it comes from looking about, so I want to sum where x sub alpha is an orthonormal basis. I'm summing over alpha, beta, and gamma, where x sub alpha is an orthonormal basis for pi, x sub betas run through an orthonormal basis for pj, and x sub gamma runs through an orthonormal basis for pk. And it's not hard to show that this is actually symmetric in all three IJK. So, and it's going to be greater than or equal to 0. And equal to 0 if, the bracket of pi and pj does not land inside, does not hit at all pk. Okay, so before I move on, the idea, where we are at here is the sort of, a lot of the Lie algebra information is right here in the symmetric triple, right? And then we have our x sub i's. And in particular, what this means is that this whole enterprise is the complexity comes from the number of summands, right? It's because sort of, more variables, right? More stuff happening, right? As opposed to the dimension of the manifold, right? So it's sort of these are the free parameters, really. And although I'm saying free parameters, there's an extra condition, and it'll pop up here and there, and that is the volume one. So we just do sort of a normalization thing. We can always reduce by 1. All right. So, and along those lines, see if that makes sense. All right. So I have a homogeneous space. So if my homogeneous space is isotropy irreducible, right, then up to scaling, there's only one equivariant intertwining map, right? And P, so P is P1, and if you say unit volume, there's a unique unit volume G invariant metric on M, and it will be Einstein, essentially, because the Ricci curvature has to do that same job. Okay, so by the add H equivariance, our L will be a scalar metric. So that was, and this is very well known. All right, the two summand case, when you have two summands, it's sort of the next level of complexity, right? And if you have two summands, then you actually have a once you think about restricting the volume, you have a one-dimensional moduli space, all right? Or I can I can write the scalar curvature as a function of one variable. So one way to get two summands is if H is maximal, but we get two summands, mostly maximal, we think that it's going to be isotropy irreducible, but not always. All right, so H can be maximal inside G, or there can be an intermediate subgroup between H and G. And what happens in these cases is that the scalar curvature's derivative will be a cubic in the maximal case or a quadratic in the intermediate subgroup case. In both cases, we know that sort of as our parameter starts at 0, S prime is positive. When H is maximal in G, we know that as T gets very large, that S prime goes to minus infinity. So we know we have at least one. We have, 1, 2, or 3 solutions, right? And those will be their critical points, and they will be Einstein metrics. If H is not maximal inside G, this is a quadratic. And if it's quadratic, then, and we know that as T gets large, S prime goes off to plus infinity. So it comes from a positive number, goes off to plus infinity. So we have 0, 1, or 2 solutions in this case. All right, so we sort of have this when we you get a little, but you can imagine that this gets, trickier, all right, with more summands. All right, but we're looking for critical points, and we can use this idea of like when things get very big. All right, so if I think more generally, not about the number of summands, but just generally, right? If I have an intermediate subgroup, right, then as long as K mod H is not a torus, so it's not flat, it's got some positive curvature, I have this Riemannian submersion, and I can shrink along the fibers. And if I shrink along the fibers, that's going to make the scalar curvature get very large. All right. If I have an H inside of multiple Ks, right, maybe I can do this in multiple ways. I can think about the sort of where the scalar curvature is getting very large. And if I cut it off at a large number, do I have disjoint components? If I have disjoint components, there must be critical points in between them. This is basically the idea behind graph theorem of Christoph Bohm and Mackenzie Wang and Wolfgang Ziller, but also Christoph Bohm has much more work along these lines. So I'm going to give us a picture of a scalar curvature functional where we have 2 parameters going on just to sort of show, right? Sort of think about like high energy level here, high energy level here, high energy level here, and they're looking sort of separated there. The whole moduli space is connected, but this idea of, between 2 high energy levels, right? We're going to have critical points, right? We can see 2 critical points in this example. This is not one of my examples. It's just a nice picture. So, but that illustrates this idea, and that's the idea behind these 2 theorems that we have these global detectors, right? So theorem of Christoph Bohm from 2004 says if you have a compact homogeneous space where G and H are connected, he creates a simplicial complex that is basically doing some, counting and, based on the intermediate subgroups between H and G. All right. And if that simplicial complex is non-contractible, then we know there's at least one G invariant Einstein metric. So the simplicial complex is telling us that we're going to have critical points. Okay. So if it's non-contractible. All right. In 2012, Mikhail Grev sort of amended this a little bit. He has a slightly simpler proof and maybe slightly more sensitive simplicial complex he calls the nerve. With a similar idea, though. If the nerve is non-contractible, then G mod H admits a G invariant Einstein metric. Okay, so these are both super nice tools. They say that it's sufficient, right? So if this nerve or your simplicial complex is non-contractible, then that's sufficient to know that there's an Einstein metric. All right. And that is to sort of avoid the deep dive into a particular space, right, that you can do with that scalar curvature functional and the x sub i's. Right. You can say, well, we can do this sort of, look at a whole families of examples sort of faster. All right. Okay. So these are amazing results. Okay. But they're not as discerning as we would like. So they're sufficient, but they're not necessary, as I'll show here. So I'm gonna, as a sort of to get an inquiry started, I'm going to take the easy case where the rank of H and the rank of G are equal. And in that case, I don't need to distinguish between the nerve and the simplicial complex. I'll just think of it as a simplicial complex. I realized as I was doing this that the rank of a Lie group is the size of the dimension of its maximal torus. So, or on the Lie algebra level, if you like, the dimension of the Cartan subalgebra, just to say what the rank is. All right, so in particular, in his dissertation, Christian Rouse classified the homogeneous spaces for G compact simple, H having equal rank, and not that's just he's just sort of putting that down. But then what he did was for each space, he worked out whether or not the simplicial complex is contractible. So this is already out there and incredibly useful. Okay. And then separate from that, it's past work of Will Dickinson and me with help and corrections from Chenju He and Jorge Lorette, that Einstein metrics on the homogeneous spaces with two isotropy summands, so G compact simple. So these are classified. All right, so we have sort of this data set, right? We have two data sets if we like. So in particular, what that means though, is we can see among the two summand spaces, we see several examples of spaces with equal rank, contractible simplicial complex. And then they do have G invariant Einstein metrics. So the simplicial complex is not telling us that we're going to have some Einstein metrics, but we do get Einstein metrics. And so here is a little table of that. Okay, so these are G is compact simple, H has equal rank. All right, and the simplicial complex is contractible, and this is a two summand space. The isotropy representation has two summands. Okay, all right. And in all of these, this is a total of 10 examples. Notice there's only one example with non-existence here. All right, and then in this table, so I said classified, but that's not exactly true because when H is maximal and E8 mod SU5 SU5 is an example, SU5 SU5 is maximal inside E8. So we know there exists at least one Einstein metric, but we don't know how many Einstein metrics there are on that homogeneous space. I don't think someone else has done that, although I don't want to go on record to my knowledge. But there's at least one. So, and these are all in this contractible simplicial complex. But, we have 10 spaces here, and actually 2 of them are infinite families. And in 9 out of 10 of these, we're still getting an Einstein metric. So that goal, like, what a criterion that's going to tell us when we have an Einstein metric, right, we'd really like to sort of improve this. So maybe an algebraic criterion. I don't think I explicitly said, but the way that the two summand classification happened was thinking about that. Remember the two summand with the intermediate group, right? It's a quadratic, so you look at the discriminant, right? And that can tell you whether or not there are 2 roots or 1 root or 0 roots, right? So critical points. Okay. All right. So our project was looking at these spaces. So G is compact, simple, simply connected. H is a subgroup of G with equal rank, and we're interested in the case with the big question marks, right? So if the simplicial complex is contractible, so it's not telling us what it's not guaranteeing us the existence of an Einstein metric. We want to look at the 3 summand, and so our project was to, with a limited idea, look at the 3 summand and 4 summand cases, and understand what happens there, and try to sort of identify something about the algebra that maybe can, is transferable in a broader setting. Okay. So on the one hand, for solving for critical points, this is more and more variables. And on the other hand, it turns out 3 and 4 are also very small. So if I want 3 summands and I think about quotients of a classical Lie group, then these are the 3 families that I can have, and they look like SUN with a quotient of a product of 3 UNs, right? All fixed to have determinant 1, right? So the sum of the K sub i's is the N, right? So we think of these as 3 blocks along the diagonal inside of SUN, and then SON with 3 blocks. I want full rank, so it'd be even, even, and then anything. It's gonna be even, 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 or even, even, odd. But if you had 2 odds, you would not have full rank. All right, but SON mod, a product of 3, or SPN mod a product of 3. Okay, but so that's how you can get 3 summands, so exactly 3 summands in the isotropic representation where G is classical, and H is full rank. Okay, all right. But one of the outcomes of Rouse's dissertation is that the simplicial complex is contractible. So non-contractible means that you know that there's an Einstein metric. Contractible means you don't, right? And it's contractible if and only if H is of mixed type, all right? And the idea of mixed type is maybe like we would replace one of these SPK1 with a U1, right? Or SO2K1 with the U1 inside there, so that there's like, so these are some orthogonal subgroup components, some unitary, right? Or some symplectic, some unitary, right? So none of these is mixed type, all right? And that means that for all of them, the simplicial complex is non-contractible. So we know G admits homogeneous Einstein metrics, but they're not in the case that we want to look at. Okay. Now, what about for the exceptional Lie groups? For exceptional Lie groups, if you want a contractible simplicial complex and equal rank and more than 2 summands, the only thing in there is H equals T2, but there you get 6 summands. For F4, we do get one example with a contractible simplicial complex. So one, rank 4 subgroup of F4. There it is. F4 mod spin 5 spin 4. And then for E6, E7, E8 with a contractible simplicial complex and more than 2 summands, there are at least 4 summands. Okay, out of those guys. So I want to tell us a little bit about F4 mod spin 5 spin 4. And the way that we go through this is we do think about those intermediate subgroups. All right, so I'm going to be very blithe. We do a lot of this on the Lie algebra level, so you can let's see what I want to say. So we have 2 intermediate subgroups here, right? And one of them is spin 9, which is maximal in F4, and F4 mod spin 9 is the compact Cayley projective plane. Just to say it, right? And our spin 5 is the double cover of SO5, but SO5, or let's do it this way, spin 5 is isomorphic to SP2. Spin 4 is the double cover of SO4. SO4 is double covered by those 2 S3s, which you can think of as SP1, SP1. It's convenient for this interpretation. You could think of them as SU2, SU2, however you want to do that. So our H is, we can also think of as SP2, SP1, SP1 when we think about it sitting inside SP3, SP1, which is also maximal, and F4 mod SP3, SP1 is also a symmetric space. Okay, all right. This actually sort of, I think, helps keep the number of summands low. All right. So this is a fibration. The base is F4 mod spin 9. F4 mod spin 554 is my space, right, that I'm thinking about, that I'm focusing on. And the fibers are orthogonal Grassmannian, right? This is actually, SO9 mod SO5, SO4. It's a good way to think about that. Okay. All right. So I have this intermediate sub algebra, spin 9, which is A plus P1, and I know that this is isotropy irreducible. F4 mod spin 9 is irreducible with respect to spin 9, and then my task is to understand what happens when the representation on this space gets restricted to our H. Okay. And one of the ways to do this, there's sort of I don't know, lazy person's idea, effective, is to use the other fibration. So because we have it. So there's our other fibration, and my fibers are sp3, sp2, sp1. So that is a quaternionic Grassmannian or symplectic, right? And then here's my space again, but now I've written my H, right? Just to sort of conveniently think of it as these symplectic groups. So F4 mod H, right? And my base is this other symmetric space, F4 mod sp3, sp1. Okay, so which is this quaternionic projector space. Okay, so now my isotropy representation, if I put those two together, has three components. All right, and what I know is if I think about H looking like SO5 and then SP1, SP1, the Lie algebra, right? Then this sum of the SP1, SP1 is my SO4, and P1 is the orthogonal Grassmannian fiber direction, right? So it looks like a row 5 external tensor row 4. P2 and P3 look like we should think about these in terms of H and its, sort of SP to SP1, SP1 version. So it looks like nu4, nu2 identity and nu4 identity nu2 for P2 and P3. Okay. One of the things that so now I've identified my representation and it's three summands. And I know, for example, their dimensions, they are 20 here and 8 and 8. I know a lot about where the Lie brackets of things live because of the subalgebras. And I don't have the most helpful picture here, I'm sorry, but yeah, so P1 was along a fiber. The fiber was a symmetric space. So P1 bracketed with itself just lands inside H. In the other fibration, this one, P2 is tangent to the fiber, and it's a symmetric space. So P2 bracketed with itself lands inside H. P3 back at P3 is always tangent to the base in our two fibrations, but each of our fibrations was a symmetric space. So it should land inside, I'll say, K1 and K2, but their intersection is H. The only, well, actually, of course, we have all the symmetric parts of the triples, but I need to really just look at how P1 and P2 bracket together. And that tells me how they land inside H plus P3. And so there's only one non-zero symmetric triple. It's definitely symmetric triple. And we can compute that. It's also easy to work inside F4. So it's a good moment to say it was very helpful to use a paper on Lie brackets of F4 using the octonions, a paper of Andreas Kollross. So that gave us a toehold into an exceptional Lie algebra. And there's the symmetric triple, it's 40, scalar curvature. This is just plugging that data. This is D1, D2, D3. 18 is my B1, B2, B3, right? And then 40 is my symmetric triple. And I can write the scalar curvature in terms of x1 and x2 and x3. Here it is. We need to take the partial derivatives, set them equal to 0. We can sort of, homogenize using our volume 1 constraint. So we get two variables. They look like Z2 is x2 over x1 and Z3 is x3 over x1. And then our system has these two equations. So we find two critical points, but actually they're isometric to each other. If you just take a look, they just exchange the values. The first one has, Z2 and Z3, and the second one, Z3 is what was Z2, and Z2 is what was Z3. And we know that there's a triality going on here. Sort of, spin 9, we know has all that going on in the octonians. And so there's an external automorphism indeed. And so, what we can see that these are isometric because remember that P2 and P3 both are 8-dimensional. All right. So we have at least one invariant Einstein metric. The fact that we have that external automorphism, it means we don't exactly have the irreducible summands P2 and P3. They are equivalent. And so, but there isn't a circle's worth of equivalences. But anyway, so we definitely have, oh, sorry. What did I just do? At least one Einstein metric. Well, let's see. I just make this big again. Sorry. Let's see. Should be plus, right? Here we go. Okay. Okay. All right. So yeah, that was a unique 3-summand example. We did get existence. So again, the simplicial complex is not everything. All right. With 4 summands, these are the quotients with the classical G. So simple Lie groups that are classical Lie groups, subgroups that have full rank. And so the quotient space has 4 isotropic summands. And then this is just a little list where we have the contractible simplicial complex. So no guarantees from the simplicial complex, right? And indeed, so here you can exactly see what mixed is, right? Is the UM and SO 2K, right? Inside of a big SO group, right? Inside a big XXSO group, you could take a UM and then two P's, a P and a Q, that is, right? SOP plus 4, we think about U1, SOP. I think actually if P were 2 here, you really have U1, but that's okay. And in that case, the simplicial complex is non-contractible, but for P bigger than that, it would be contractible. This is actually the one case that's known. This is a flag manifold, right? And so Andreas Arvanitiorgos and Dionis Chrysikos have a paper about flag manifolds with 4 summands. And they identified 8 Einstein metrics. All right, and then there's one more. So we know that there's at least one on the first family, the second family, and the third family, and the fourth family. First, second, and fourth. We know there's at least one from numerics. This is a funny thing where there's only 3 X sub i's to worry about. But when you're computing, you have variables for M and K, right? Or M and P and Q. So it's quite a lot of variables flying around. All right. So, but we believe we have solutions in those cases, in those families. If we look at exceptionally groups with equal rank, we do get more examples. So G2 with a contractible simplicial complex, we don't get anything. F4 has one example. So for summands, if you notice this F4, this looks a lot like our three-summand example, right? Our three-summand example was F4 mod SP2, SP1, SP1. And here we're just taking one of those SP1s and shrinking it down to U1. All right. And actually, we do want it to be not the one inside SP3. All right. Okay. E6 has one quotient. All right. And that is two copies. So H has two copies of SU3. All right. And two copies of circles, U1s. All right. You can think of it as living inside SU6 and SU2, which is I think a maximal subgroup of E6, as I recall. I don't have that in front of me. All right. With E7, we think there's only one quotient of E7 with four summands. That is work in progress. And so there's a way to think about that, SO8, SO4, U1. All right. And then E8, definitely, so looking at four summands. So, and this is work in progress. Most of these have more than four summands. Like there are many examples, but there are more than four summands. But identifying, I think that's sort of, it's easy to find the full rank subgroups, and we know all about their simplicial complex. We don't always know about the number of irreducible summands. The issue here is that we're working over the reals, right? And so you think about whether some irreducible summands come in complex pairs. And the other thing is that the more these little circles we have flying around, they keep things exciting. It's a little easier when all the pieces of H are, so if H is semi-simple. All right. So I'm going to walk us through F4 mod SP2, SP1, SP1. Oh, F4, SP2, SP1, mostly to show off this beautiful diagram here and give a sense of the game. All right. So now I have all these containments. So there's sort of this algebra going on, and then the equation solving part as well. Right. So we know SP2, SP1, U1 is inside. This is our old H as spin 5, spin 4. Right. But it also sits inside SP3, U1 before we get to SP3, SP1. All right. So we had that connection before, right? And now we are thinking about, you could sort of go, first beef the SP2, SP1 up to SP3, and then go take the U1 and put it inside SP1. This is just the same combination in the opposite order. The U1 changes to an SP1, right? So U1 sits inside the SP1, it's in here. And then the spin 5 and one of the SP1s. So this is SP2, SP1. There's this spin 5, spin 4 is SP2, SP1, SP1. All right, and the first two components go into SP3. All right, but written this way, spin 5, spin 9, we can spin 5, spin 4, we can see it inside spin 9. All right, and this is the operation we have going on here. Okay, all right. So we get four summands. The first one we'll think of as just the circle, the two-dimensional circle action, right? The next one, P2, is, where'd he go? Is our spin 5, spin 4 inside spin 9, but restricted. All right. So this is the orthogonal Grassmannian action. Now, and then the third piece is restricted to the U1. Right. P3, though, is the way to think about this is it does nothing on the last SP1, right? And takes the SP2, SP1 into SP3. That's P3. And then P4 in both of these cases is part of the symmetric space with F4 mod a maximal subgroup, but now restricted. Okay, to our H. All right. So one of the things we know from the diagram, maybe I'll try to illustrate one of these things here, right, is that if I think about H plus P3, I get the Lie algebra for this SP3U1. If I take H plus P3 plus P1, I get the Lie algebra for SP3, SP1. One of the things that tells me is that if I bracket P1 and P3, I'm doing Lie brackets inside of this Lie algebra SP3, SP1. So it's not going to land in P2 or P4. Right. And similarly, if you take H plus P1 plus P2, you end up with spin 9. So the brackets of P1 and P2 happen inside spin 9. They're not going to overlap with P3 or P4. All right. And we use all that to sort of work out exactly which of our symmetric triples will be non-zero. And again, with great thanks to Andreas Kohlrose. This is out there, but it's difficult, right? So trying to think about computing Lie brackets inside of an exceptional Lie algebra. So this is a new skill for us. All right. And so we had 3 non-zero symmetric triples. And so we are working on this example. It's actually in progress. And then and even the classification of the spaces, quotients of E8 with exactly 4 summands. It's a short list, but it's in progress. So thank you for listening.
Thank you, Professor Kerr. Very interesting talk. People are reacting. And now we are open for questions. If you want to participate, just raise your hand virtually and we will allow you to unmute yourselves. So we just or maybe I can allow people to unmute themselves. No. Everybody's allowed to unmute if anyone want to participate. Okay, maybe I can start with a question. I think I want to know, it's not about this exactly what you said, but I want to know if there is, as your knowledge, some criteria for existence of Einstein metrics in, for example, cohomogeneity one manifolds.
Yeah.
Some topological restrictions, because I think that, for example, that criteria from Bonda, making the simplex,
Yeah.
maybe that depends on the homogeneous space structure, but I don't know if there is something analogous for less symmetries.
But you want to, I mean, what I think is really, you're just at, like, you would still, you don't need Einstein, right? But your metrics would do what they do on the orbits, right? So
Yeah,
you have those parameters, right? And then T, right?
exactly.
Yeah,
It's
yeah, yeah.
invariant, but the action is not transitive. And if you have some criteria in that context.
Yeah, I don't know that much about that. So I know it's
Okay.
like a sort of
Okay,
sometimes disk bundle work, right?
okay.
But
And another question I have, maybe I was expecting, because there is a conjecture about the number of Einstein metrics on a compact homogeneous manifold with inequivalent isotropy summands. I wish to know what do you think about what is your intuition about that conjecture?
Let's see. So we know, I mean, okay, what do I know? Everything has to be qualified. Okay. All right, there's new work, right, on this, but it's the context, right? So inequivalent summands, that keeps things simple, but you were not worrying about the rank. You said inequivalent summands, right?
Mhm.
Right, and then I mean there's a new paper on this, right, on the archive of I'm blanking of well, okay, no peeking. Anyway, there's a new paper on this. It is an upper bound sort of on analysis things, right? I mean, it would be you would think that this is sort of algebraic geometry, right? The issue is negative solutions, complex solutions, right? So, um, an equivalent summand should help a lot, right? I think the other thing full rank does is make sure there's not another like commuting circle, right? So,
But it is there exists an upper bound with the number of
yeah,
asymmetries.
I think
Uh,
so. Yeah, yeah.
and it has any restriction or compact homogeneous manifold with inequivalent summands generally.
Um, I'm not sure. So, yeah, yeah. I mean, I think the other, I'm sure you know, right? Right. It's that the sort of seven sphere idea, right? Is that depending on the H embedding or the H action, right? You get sort of, different differentiable structures. And so you get different metrics. So depending on how you think of it on the same space, right? You
Okay.
you can get many examples, but you're really, you know, maybe they're not on the same diffeomorphism space. I'm not exactly sure.
Okay, Professor.
But yeah, I think if you okay, I just shouldn't. I'm not very good at answering questions I didn't think about.
Okay. Okay, Professor. Thank you. Thank you for the interesting talk. Any more questions? There's a question here. You can mute yourself. One.
Uh, Thank you, Professor, for your nice presentation. Uh, in slide number 14, what is the difference between zero and non-zero Einstein matrix?
That's the quantity, right? So
What they
uh,
refer?
so
What is
most
the
of these
difference?
spaces admit two. One of them admits at least one. Only one of them admits none. So
What they actually uh, uh, refer uh, in reality?
say that again?
What
Can
they
you?
refer actually in practically zero and non-zero meaning of Einstein matrix.
I guess that question of sort of like this is an example. I cannot say too much about what it looks like. E7 mod spin 6 SP1, right? It has two isotropy summands, right? So not a lot going on. It does not admit an Einstein metric. So a G invariant Einstein metric. And that's so that question of like what made that be non-existent, this is in the two-summand case, we know there's a quadratic, right? Does that quadratic have roots, right? So the discriminant is negative. The answer is no, right? But what made that happen? I don't know.
Thank you for
Yeah. I mean, one of the things about some of the infinite families in the two-summand paper is that it switches depending on, so without this equal rank or non-contractible, it switches, without equal rank, really. That having solutions, not having solutions, that switches when, one of the like M or if I look at, SOK plus 2M, when one of those things gets big enough, right, then it goes from, I think, existence to non-existence. But anyway, it depends on those numbers. Does that help?
Thank you.
Yeah.
Yeah, so hi Megan, this is Jason Lote here asking a question. So I just wanted to ask, what do you think are the limits of this type of analysis? I mean, you could up the number of summands and stuff, but at some point this is probably going to become unwieldy. Is there some
Oh, yeah.
upper bound to this, or do you think it's just going to become numerical and maybe you have to do some rigorous numerics, or what do you think is the sort of future? Where does the future hold for the sort of homogeneous stuff?
Yeah, really, the hope is that, I mean, somehow 3 and 4, there are not that many examples, but I don't really think of like the, sort of pushing the boundary there as being super useful, but trying to kind of go from that nice discriminant for two summands and trying to identify something in the 3 and 4 cases would be, that's really, it's like, well, what are we seeing happening, right? So, the goal is some kind of algebraic, more algebraic, maybe obstructions, right? Something like that. Yeah. Yeah, that would make more sense than I mean, I will say that like the 2 classification seems like it's a great family of examples with information, but that's sort of what it provides, I think, mostly, right? So
Yeah. Okay. That sounds great. And do you think that what you're doing, your sort of work in progress, does it hint that there is such a nice algebraic way to see it, or is it random? Does it really seem like sometimes they do,
it's
sometimes
hard
they don't?
to I don't think we're really seeing something very, very effectively. But maybe we haven't played around with it enough. So
Yeah, it's obviously very difficult, but it's very
yeah.
nice. Yeah.
Yeah. I mean, the other question is, this is, very much, we are keeping things easy by keeping the rank of H equal to the rank of G, right? So you could look at the number of summands without that, but and then just, maybe that would add more to the data.
Yeah, I think that would be very interesting.
Yeah.
Well, thank you very much.
Thank you.
Okay, thank you. I think no more questions. So let's thank again Professor Kerr. Thank you for being here.
Yeah.
Again, I hope you can participate in future initiatives like this one.
Oh, thank you very much.
And now we are going to our next talk. Let me see if I think Nicoleta is here already.
Yeah, there. Hi.
Hi, nice to meet you.
Nice to meet you.
Thank you for being here. Thank you for accepting our invitation.
Thank you for inviting me. Yeah. Thank you.
We will start in, I think we will start in 7 minutes, but we can check if you can share your screen, your slides.
Sharing, yes.
Some
See.
technical issues.
See, 1 second. Okay.
Sorry, I have to. You can share. Okay. Let me make you copies of the. Okay.
Can you see my screen?
Yes. Perfect.
Oh, cannot change. Okay, maybe I can do like this. Okay. Is it working?
Yes. Yes,
Okay.
yes, it's working well. Okay, so let's wait a few minutes.
Of course, yes.
Juliet is not here in the morning, but
Mhm.
in the afternoon, she's going to be here. Nicoleta, I think,
Yes.
can you put it in full screen?
No, that's the problem. I don't understand.
Oh,
Change because it changed a little bit the screen. So let me see. Maybe like now, maybe.
yes, 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 it is working. It is on full screen now.
It is on full screen, but now I cannot change the page.
No,
So-
then I think it's
Okay,
better.
so let me try this again. So I will stop sharing. And let me try this differently. So maybe. Okay, so let's try like this. No, I cannot change the page. I don't
Okay,
understand.
then no
So,
problem. I think it's enough with.
okay, so now if I have a few minutes, maybe I can try and fix this.
We have that. We have
It's-
three more minutes.
So maybe I will share the whole screen. So now I can do like this. And this
Okay,
works. Okay, perfect.
good.
Okay,
Thank you, thank you.
thank you.
Oh, Nicoleta, we are recording the event and we're live
Yes.
on YouTube. Are you okay with that?
Yeah, no problem. Yeah.
Okay, thank you. Okay. I think we can start now. Let's start with the nice talk by Nicoleta Tardini. She's going to talk about pluriclosed manifolds with parallel bismuth torsion. Thank you for accepting our invitation again. Thank you for being here. To all the participants, thank you again, and you can go ahead when you're ready.
Thank you very much. Thank you very much for the invitation. I mean, it's an honor to be here and have the possibility to give this talk. So I would like to present some results obtained in collaboration with Giuseppe Barbaro from the University of Aarhus and Francesco Pediconi from the Politecnico di Torino about a special class of Hermitian matrix on complex manifolds. And we will see that these matrices have very, very nice symmetries. Okay. Okay, but now I cannot change again. I don't know why it's not working, so maybe. Is it working now?
Yes, it is working.
Okay, perfect. So the talk is divided into parts. So in the first part of the talk, I will recall the base, let's say the main definitions and results about this class of special Hermitian matrices that are called pluriclosed matrices on complex manifolds. And then in the second part of the talk, I will focus my attention on a subclass of these matrices that have nice curvature symmetries, okay? They will have Kähler-like symmetries. Okay, again, it's not working. I don't understand. No. Okay, maybe we can do like this. So the setting, again, is Hermitian geometry. So let me recall, at least for my notation, what an Hermitian manifold is. So during the whole talk, M will denote a smooth manifold of real dimension 2n. And on this manifold, this smooth manifold, we have three geometric structures, okay? So first of all, we have a complex structure. Okay, so for me, a complex structure is a 1-1 tensor, so it's an endomorphism of the tangent bundle that squares to minus the identity, okay? But this is not enough to have local holomorphic coordinates, okay? So having a tensor with this property is not enough to ensure that locally our manifold is modeled on Cn. So we need an additional condition that is called integrability condition. This can be expressed in several equivalent ways, but the point is that thanks to this condition, we know that locally we have holomorphic coordinates, okay? So we are on a genuine complex manifold. And then I will denote with G an Hermitian matrix. So an Hermitian matrix is a Riemannian matrix that is compatible with the complex structure in this way. So J is essentially an isometry for the metric G. And finally, we have on a Hermitian manifold, we have the so-called fundamental form. So the fundamental form, you can think of it as a two-form. So it's a real two-form on the manifold M that is defined in this way. You use the metric G and the complex structure J in this way, and you define this two-form, differential two-form. And in fact, this two-form has a special B degree, has B degree 1-1, because the existence of J on the smooth manifold induces on the space of complex value differential forms a natural B degree. And I will not stress on this because, I mean, it's not important in this talk, but with respect to this B degree, actually, omega has B degree 1-1. Okay, but if you're not familiar with complex geometry, you can think of omega as a real two-form positive in the sense that it's defined through a Riemannian metric and Hermitian metric in this way. And usually people in Hermitian geometry actually call omega itself Hermitian metric, okay? So sometimes during this talk, I will call omega Hermitian metric. And actually every time you are given two of these three structures, you can recover the third one, okay? So omega for us today will be the Hermitian metric, okay? So it's a differential two-form. And among Hermitian metrics, of course, we have, some metrics that are more special than others. So for instance, probably some of the most special metrics we can consider are Kähler metrics. So a Kähler metric is a Hermitian metric such that the fundamental form omega is closed. So actually, this is a symplectic structure now, okay? So in fact, a Kähler metric is the datum of a symplectic structure compatible with a complex structure. And so essentially, in Kähler geometry, we have these three structures you see that are compatible. So we have a complex structure, so we have complex geometry, all the tools from complex geometry. We have a Riemannian structure, so all the tools coming from Riemannian geometry. And then we have a symplectic structure, okay? So this means that all the tools coming from symplectic geometry. So we have these three geometries that are related. And so, of course, this means that we have of course, several nice results, but also some very strong results and strong restrictions for the existence of these metrics. And in fact, the Kähler condition is equivalent to us this fact. So if you take the Levi-Civita connection of the Riemannian metric, that actually you see you have that the complex structure J is parallel with respect to the Levi-Civita connection on Kähler manifolds, okay? So this is an if and only if. So you see also through this relation that we have a nice compatibility between Riemannian geometry and complex geometry. And as I was mentioning, so this leads to several nice results, but also strong results. So we have several obstructions to the existence of Kähler metrics on complex manifolds. And in fact, we have actually also topological obstructions. For instance, the even Betti numbers are positive because we have a symplectic structure, but also the odd Betti numbers are even. This comes from Hodge theory. And so this is just to say that, we have a lot of Kähler manifolds. For instance, every complex algebraic manifold is scalar. But in fact, there are also a lot of manifolds, complex manifolds, that do not have any Kähler metric, okay? And so for me, the goal is somehow to investigate these manifolds, okay? The manifolds that do not have Kähler metrics. So investigate the geometry of Hermitian non-Kähler manifolds, okay? So in the case where omega is not closed. Okay, so during the talk, so I will fix on Hermitian manifolds. In general, so non-Kähler, okay? So I do not want J to be parallel with respect to the Levi-Civita connection. But also this means that the Levi-Civita connection is not a good connection, right? To study Hermitian geometry because it's not preserving the complex structure. So it is kind of natural for this reason to consider different connections that preserves the Hermitian structure. So an affine connection is called Hermitian if it preserves the Hermitian structure, okay? So it preserves both the metric and the complex structure, okay? But of course, so this is a metric connection, but it will not coincide with the Levi-Civita connection in general. So this means that this connection will have torsion, okay? And among Hermitian connections, actually, we have a very, let's say, special class that was considered by Goduchon because it proved that we have an affine line of canonical Hermitian connections that is described by this formula, okay? So, so let me say a few things about this formula. So T is a real parameter. So these connections, nabla T, are defined through the Levi-Civita connection in this way. So here we have, you see the dc of omega appearing here and here. So this operator, dc, is a differential operator, okay? So it's on differential forms. So it's defined using the exterior derivative, so the usual differential operator d. And this operator is twisted using the complex structure J, okay? Because, of course, by definition, the complex structure is acting on vector fields, but of course, you can dually induce an action of the complex structure on forms, on differential forms. So you can So then this definition makes sense, okay? And C, if you want, stands for complex, okay? So we have this DC operator here. And here again, you see we have omega appearing. So omega is our Hermitian metric, okay? And okay, so we have this formula. And you see that of course, the first thing you can think of is, okay, what happens when t is equal 1 and t is equal -1? Because we can get rid of these two terms, right? So, so what we have is that in case t is equal 1, we have the so-called Chern connection, okay? So the Chern connection is a very important connection in Hermitian geometry, and it corresponds to the case where t is equal 1 t equal 1, so we don't have this term, okay? But at least for this talk, actually, I'm interested in the bismuth connection that corresponds to t equal -1. Okay, so the bismuth connection appear when t is equal -1. So we don't have this term, this last term. Okay, we only have this one. And in fact, the bismuth connection can be actually also equivalently defined, saying that it's the unique Hermitian connection. Okay, so it preserves the metric and the complex structure. And also the torsion of this connection is totally skew-symmetric. So what does it mean? It means that if you consider, so for me, TB is the torsion tensor of this connection, nabla B, the bismuth connection. So if you put TB here in the metric, G is our metric, and you define this tensor here, it is actually skew-symmetric. So this is a differential 3 form in case of the bismuth connection, okay? So in this talk, I'm interested in this connection. Again, what happens when omega is scalar? So when omega is scalar, omega is closed, okay? So actually this means that DC omega is actually 0. So all these connections actually collapse to the Levi-Civita connection, okay? They coincide with the Levi-Civita connection, okay? For any t. So, okay, so but when omega is non-scalar, these connections are, of course, different. Okay, so actually we can be even more precise. So the torsion of the bismuth connection is not just any 3 form. So actually is exactly minus dc of omega, okay? So omega is a 2 form, as we said. dc is a differential operator. It increases the degree by 1. And so this is our 3 form. And this 3 form is not closed in general. So here is actually the definition, our, let's say, main definition for this talk. So what is a pluriclosed metric? So an Hermitian metric, omega, is called pluriclosed if the torsion of the bismuth connection is closed. Okay, so this means that this equation is satisfied. So the differential of the torsion is 0, or equivalently, since we have this relation, I'm saying that omega is DDC closed. And well, if you're familiar with complex geometry, this is equivalent to say that omega is DD bar closed. Okay, so here is probably the motivation for the definition pluriclosed. Actually, these metrics sometimes in the literature are called strong scalar with torsion, so SKT. Well, that is a terminology coming mainly from physics. But yeah, so SKT metrics are exactly pluriclosed metrics, okay? And again, this is, if you want, a possible generalization of the Kähler condition, because if you have a Kähler metric, omega is D-closed, so in particular, it is DDC closed, okay? So this equation is automatically satisfied, okay? So you can think of pluriclosed metrics, if you want, as a generalization of Kähler metrics. Okay, but in fact, we have several generalization of the Kähler condition in complex geometry, in Hermitian geometry. And one of them, so an important class of this other special Hermitian metrics is given by Goduchon metrics. So let me record briefly this definition. So an Hermitian metric is called Goduchon. Actually, so these metrics were introduced by Goduchon, and he called them standard. And now we call these metrics actually with his name, so Goduchon. If this equation is satisfied. So what do we have here? So I'm taking omega. Again, omega is a two-form. I'm taking the wedge product of omega with itself, n minus 1 times. So this is a 2n minus 2 form. And then I apply the two differential operators, d, dc, okay? And I want these to be 0. So these are Goduchon metrics. So why I'm talking about this? Because you see, when n is equal to, so if we are on a complex surface, okay, so real dimension 4, Goduchon metrics exactly coincide with pluriclose metrics, okay? So because if n is equal to, this equation reduces exactly to the equation ddc omega 0, and ddc omega equals 0 was the equation for pluriclose metrics, okay? So on surfaces, Goduchon metrics coincide with pluriclose metrics. And the point is that Goduchon proved that Goduchon metrics always exist on compact complex on compact complex manifolds. So the result is this. So if you have a compact complex manifold of dimension, say, greater than 1, okay, of complex dimension greater than 1, then Goduchon metrics always exist. And actually, they exist and they are unique up to multiplication with positive constants in the conformal class of any Hermitian metric. Okay, so not they exist, but in fact, you can say more. You can say that if you pick an arbitrary Hermitian metric, and then you look in the conformal class of this metric, then in this class you can find a Goduchon metric. Okay, and actually this Goduchon metric is unique up to constants. Okay, so this is a very strong result. And in fact, this means that pluriclose metrics exist on every compact complex surface. Okay. But of course, this will not be true in general in higher dimension. Okay, we cannot expect in general pluriclose metrics to exist on every compact complex manifold. So here, let me say a few things about examples. So, of course, I mean, it's kind of natural to look for higher dimensional non-killer examples of pluriclose manifolds. In this list, we have here, I mean, there are some results. Of course, it's not an exhaustive list. I mean, there is a very rich literature about pluriclose manifolds and pluriclose metrics. So here, just a few results. So first of all, let me say that if you have an even dimensional compact Lie group with a left invariant complex structure, so a Samuelson complex structure, and you have a compatible B-invariant metric, then this B-invariant metric is pluriclose, is always pluriclose. And actually, you can construct pluriclose metrics on products of three-dimensional Sasaki manifolds, as proven by Andrade and Tolkachier. So if you take, let's say, two three-dimensional Sasaki manifolds, and you take their product, there is a natural way to construct a complex structure on this product. And then, in fact, if you take the metric product of the two Sasaki metrics, actually this metric will be pluriclose. It's compatible with the complex structure and it is pluriclose. And then there are a lot of results concerning quotients of nilpotent Lie groups and solvable Lie groups by lattices. So in fact, in Hermitian geometry, a very important source of examples is given by nilpotent Lie groups, or if you want more in general, solvable Lie groups, connected and simply connected. And then you quotient by lattices, so you construct these manifolds that are usually called nil manifolds and solve manifolds. And sometimes when you can construct on these manifolds left invariant complex structures, so invariant complex structures on the manifolds, so coming from the Lie algebra of the Lie group, So actually, these manifolds really provide a lot of important non-Kähler examples. In fact, nil manifolds can never be Kähler unless they are torized. So this is just to say that if you want to construct non-Kähler complex manifold, I mean, a good point where to start is starting from nilpotent Lie groups, okay, or solvable Lie groups, and then construct these nil manifolds and some manifolds. And in this case, especially in low dimension, we have classifications. And using that, for instance, so let's look at this result by Finoparton-Salamon. Actually, so they classified the 6-dimensional nilpotent Lie algebras with a complex structure and a pluriclose metric. Okay, and in particular, in this case, it is interesting because the existence of a pluriclose metric compatible with a complex structure depends only on the complex structure. So in fact, what they show that in this particular case of the six-dimensional nilpotent nil manifolds, they actually have that either all the metrics are pluriclosed or none of the metric is pluriclosed. And then we have also some characterizations on almost abelian Lie groups and so on. I mean, there are a lot of examples, let's say, concerning Lie groups and quotients of Lie groups. Also, there are some techniques to construct new examples starting from, the known ones. For instance, Finn and Tomassini proved that if you have a manifold minus a point with a pluriclose metric, that actually you can extend this metric to a pluriclose metric on the whole manifold, okay? And so there is this extension result, like in the Kähler case. And then they also showed that it is possible to construct new examples using blow-ups. So you can start with a compact complex manifold, and then you can blow up a point, or in fact, more in general, a submanifold, a compact complex submanifold. And if your starting manifold was pluriclosed, so with a pluriclosed metric, then the new manifold you construct is still pluriclosed. Okay, so you have this way to construct, more and more examples. But unfortunately, on the other side, you cannot construct new examples using deformations, okay, small deformations. What do I mean? I mean that, so think that you start with a compact complex manifold, okay? So you have your complex structure J, and then you deform a little bit this complex structure, okay? So if your starting complex structure was admitting a pluriclose metric, in general, if you move a little bit the complex structure, it doesn't mean that you can construct along these deformations pluriclose metrics, okay? So they showed that there are some counterexamples. And also, again, on this in this list, so let me say that the pluriclose condition is somehow complementary to another condition that is called the balanced condition. So let's say that, if you move from Kähler geometry to non-Kähler Hermitian geometry, the situation can be very wild. I mean, you can define a lot of interesting special Hermitian metrics, but of course it is a natural question to understand whether these different kinds of metric can coexist on the same manifold, okay? So for instance, now we know that we have this pluriclose matrix. Another class of important metrics are the so-called balanced metrics. So balanced metrics are defined in this way. Again, we have omega, that is the Hermitian metric. It's a two-form. I take again the product of omega with itself, the wedge product of omega with itself, n minus 1 times, and I apply the differential d. In general, for any Hermitian metric, this is equal to theta wedge omega n minus 1. So this equality is always true for any Hermitian metric, where theta is a one form, is a differential one form. It is called the Lie form of the metric. And in the balanced case, we have that actually this is 0. So d omega n minus 1 is 0. So which means that in fact, this form theta is equal to 0. And what happens is, so why I'm saying that this pluriclosed condition is complementary to the balance condition, because actually if you have a metric that is both pluriclosed and balanced, then actually it is scalar, okay? So actually it is symplectic, omega is closed. And this can be proven in several ways. For instance, you can use this formula by Alexandrov and Ivanov. So again, pluriclosed means that DDC omega is equal to 0. So here on the left-hand side of this equality, you have 0. And balanced means that theta is 0. So this is 0, this is again 0, and so you are left with the norm square of d omega, so d omega is 0, so omega is scalar, okay? So if your metric has both properties, pluriclosed and balanced, then it is in fact a Kähler metric. And this is somehow related to a more general conjecture by Finn and Bezzoni that says that in fact, if you have a compact complex manifold, this matrix, so pluriclosed matrix and balanced matrix cannot coexist. Okay, so in fact, they conjecture that if you have a pluriclosed metric and then you have another metric that is balanced, then there exists a third metric that is scalar. Okay. And in fact, this conjecture recently has been extended by Ornia Verbitsky, including also locally conformally Kähler metrics. So it seems that somehow all these special metrics you can consider, they cannot coexist on non-Kähler manifolds. Okay, so this somehow it seems to be true. But I mean, everything here is again at the conjectural level. Okay. Of course, all the examples we know satisfy this, but in fact, this conjecture has been proven also in some, let's say, large classes, okay, of examples. For instance, on manifolds that are in class C of Fujiki, so when they are bimeromorphic to Kähler manifolds, they are not Kähler, but they are bimeromorphic to Kähler manifolds, it is known that they always have a balanced metric, by a result of Alessandrini and Bassanelli. But Chiose proved that if you also have a pluriclosed metric, then actually you have a Kähler metric. So again, the conjecture is confirmed. Then Finn and Bezzoni, in the paper where they gave this conjecture, they prove that it is true on nil manifolds. Okay, so on quotients of simply connected nilpotently groups by lattices with invariant complex structures, okay? And also in some special low-dimensional submanifolds. And then, of course, this conjecture has been checked on many other examples, on almost abelian submanifolds, Oye-Claussama manifolds, and so on. So in fact, every time you have a new example of a non-Kähler manifold, people look for, they try to see whether this conjecture holds, okay? All right, so this was just to give an overview about a pluriclosed matrix, okay? So we have a lot of examples of this pluriclosed matrix. And they were related to the bismuth connection that was defined through the Levi-Civita connection of the metric through this formula, okay? So this was the result of Duchamp. And again, the bismuth connection does not coincide with the Levi-Civita connection, okay? So the bismuth connection has torsion unless the metric is scalar, but we are interested in non-Kähler metrics. Okay, so for this reason, so since the bismuth connection does not coincide with the Levi-Civita connection, we cannot expect, all the nice symmetries we have for the Levi-Civita connection. For instance, we don't have the first Bianchi identity. So if you consider the curvature tensor for the bismuth connection, okay, so B again for me is just to stress on the fact that I'm taking the bismuth connection, okay? So I'm taking the curvature of this connection, and then I'm considering, a cyclic sum over the first three entrances, okay, X, Y, Z. Well, this is not zero, okay? So we don't have the torsionless Bianchi identity because, again, we have torsion. So what do we have here? So we have the differential of the torsion appearing. So the torsion, if you remember, is a three-form. And this differential of the torsion is 0 when the metric is pluriclose, by definition, okay? So somehow you see here appearing the pluriclose condition in some sense. And then you also have this term, so that is related to the parallelism of the torsion appearing. Okay, so let me recall this definition that is due to Angelo Tal Ugarte via Campa. So this definition was inspired by another definition. So, but let me first give this definition because it's the general one. So suppose that you have a complex manifold and a Riemannian metric, okay? In general, this definition can be given even though the Riemannian metric is not Hermitian, okay? So a metric connection is called Kähler-like if it satisfies the first Bianchi identity, okay, so this. And then we also ask for this J invariance, if you want, in the first two entrances and second two entrances of the curvature tensor. If you have, why this connection is called Kähler-like? Because in the Kähler case, so if you have a Kähler metric, these conditions are satisfied for the Levi-Civita connection, but also for any other Hermitian connection, okay? So that's why essentially they're saying, okay, so we are asking for Kähler-like symmetries, okay, for the curvature. And this definition was in fact inspired by the definition of Yang and Zhang that was given specifically for the Levi-Civita connection and the Chen connection, okay? So in case of, if you put here the Levi-Civita connection or the Chen connection, this definition reduces to the definition of Yang and Zhang. Okay, so let me comment a little bit this definition because now I want to consider the bismuth connection, okay? So first of all, notice that if I take a Riemannian metric that is in fact Hermitian, so that satisfies this equation, and moreover, if I take a Hermitian connection, so J is parallel, then in fact, you can just really write down the definition of curvature tensor, and it's immediate to see that this is trivially satisfied, okay? So we have this J invariance here. And then if you assume that you have the first Bianchi identity, in fact, you can apply this 4 times to check that actually this is also satisfied. So actually you can swap the first 2 entrants and the second 2 entrants. You see XY, XY, ZW, ZW. Okay, so what does it mean this? This means that if I assume that I have one of the Goduchon connections, nabla T, so for instance, the bismuth connection, but in fact any other Hermitian connection, and in case this connection satisfies the first Bianchi identity, then the second equation here, line of equations, here in this definition is automatically satisfied because I have, thanks to this, I have J invariance in the last 2 entries, but then if I assume first Bianchi, I can swap the first 2 entries with the second 2 entries, so I also have J invariance in the first 2 entries, okay? So this means that the Kähler-like condition actually reduces to the first Bianchi identity, okay? So the bismuth connection will be called Kähler-like if the first Bianchi identity is satisfied, okay? Actually, in the literature, this condition has been called also Strominger Kähler-like, because sometimes I forgot to say that the bismuth connection is called Strominger connection, okay? So anyway, so I would say that an Hermitian metric is bismuth Kähler-like in case the bismuth connection is Kähler-like, okay? So we have this Kähler-like symmetry. We have this first Bianchi identity. Okay. Okay, so just a few words, in the case I'm consider not the bismuth connection, but the other connection. So if the manifold is compact, Yang and Zhang proved that if either the Levi-Civita connection or the Chen connection is Kähler-like, actually you get a balanced metric. The metric itself is balanced, okay? So you see Balanced metrics were the one defined before. I mean, you don't have to remember the definition, just think of them as special Hermitian metrics. So this means that if you have nice symmetries for the curvature, these symmetries actually implies conditions, the implied conditions on the metric, okay? And then Lafuente and Stanfield proved that if you take one of the Goduchon connections, okay, nabla T, okay, except for the Chern connection and the bismuth connection, so any other connection in the line of Goduchon, when this connection is scalar-like, then actually the metric is scalar, okay? So it seems that, again, the Chern connection and the bismuth connection are somehow more special in some sense with respect to the other connections, okay? So because in this case, we end up with a Kähler manifold, in fact. Okay, so let's consider the bismuth Kähler-like condition. So Angelo Talugarte Villacampa conjectured that if you have a bismuth Kähler-like manifold, so again, bismuth Kähler-like means that the bismuth connection has the first Bianchi identity, then the metric is pluriclosed. So this was the conjecture, and they had some evidences, of course, to this conjecture. For instance, the flat case. So if you have a bismuth flat manifold, so bismuth flat means your curvature tensor is 0, is trivial, right? So of course you have Kähler-like symmetries, and so in this case it was known that bismuth flat manifolds are pluriclosed, and in fact bismuth flat manifolds are essentially understood because Wang Yan Zhang showed that bismuth flat our manifolds are covered by, let's say, this product. So you have an Euclidean factor, and here compact semisimple Lie group K, and this is endowed with a B invariant metric and the Samuelson complex structure. Okay, so every bismuth flat manifold is covered by something like this. And then they also had, again, some examples on solved manifolds. So with Anafino, we tried to solve this conjecture. Unfortunately, we were not able to do it. But still, we saw that, so probably let me go back here. What somehow we realized is that, so the fact that bismuth Kähler-like, which means that this term is 0, is related to having, of course, a pluriclosed matrix, which means that this is 0, and also here parallelism of the torsion, so which means that this is 0. So essentially what we got, so probably let's just look at the last result. So what we proved is that if you have a bismuth Kähler-like metric, so we have first Bianchi identity, then we are not able to prove that the metric is pluriclosed, but we can say that the metric is pluriclosed if and only if the torsion is parallel with respect to the bismuth connection. Okay, so we have these two equivalent conditions. And this was done using, say, some intrinsic formulas involving all these tensors. But then, in fact, Zhang and Zhang proved the conjecture using different techniques. They use a coordinate approach. And actually, they prove more. They fully characterize bismuth Kähler-like metrics, because they proved that a bismuth Kähler-like metric, bismuth Kähler-like metrics, in fact, are pluriclosed metrics. So they prove the conjecture, they are pluriclosed. But in fact, they are pluriclosed and they have bismuth parallel torsion. Okay, so the torsion of the bismuth connection is parallel with respect to the bismuth connection. Okay, so the metric is Kähler-like, is bismuth Kähler-like if and only if it satisfies these two conditions. And then, in fact, they also, of course, they checked the conjecture I told you about by Fino and Bezzoni, the one that was saying, okay, if you have a non-Kähler manifold, pluriclosed matrix and balanced matrix cannot coexist. And so they did not prove the conjecture, but since these manifolds are in particular pretty closed, they showed that on this kind of manifolds, so Bismuth-Keller-like, you cannot have balanced matrix, okay? So that showed that if you have a compact non-Keller Hermitian manifold and you have a matrix that is Bismuth-Keller-like, so you have these Keller-like symmetries, then you don't have any balanced matrix, okay? But these manifolds are pluriclosed, okay? So they confirmed again the conjecture. Okay, so yeah, I can skip this. So what are these Bismuth-Keller-like manifolds? Okay, so now we have a characterization. Okay, so nice symmetries for the curvature means that the metric is pluriclosed, and we have this additional condition. So what are these manifolds? In dimension 2, they are already known. So let me introduce again a new class of metric. So a Hermitian metric is called Weismann if it satisfies these two conditions. So it is locally conformally Keller, which means that, remember, Keller means that omega is closed, so d omega is 0. Locally conformally Keller means that d omega is equal to theta wedge omega, where theta is a d-closed one form. And actually, this definition is equivalent to say that the metric locally on your manifold, okay, so on open subsets, on your covering your manifolds, it is conformal to a Keller metric, okay? It's not globally conformal to a Keller metric, but locally it is. And in the Weismann case, we have an additional condition. We have that this one form theta is actually Levi-Civita parallel, okay? So, well, we have this class of metrics. They are very, I mean, again, also for this matrix, there is a rich literature studying this manifolds admitting Weismann matrix. In particular, Weismann matrix are always Goduchon. If you remember at the beginning of the talk, I told you about this kind of class of matrix that always exists on every compact complex manifold. And it was given by a conformal, they exist on every conformal, in every conformal class. And Weismann matrices are always Goduchon matrix. Okay, so if you have a Weismann matrix, it is the Goduchon matrix of the conformal class. And in dimension 2, what we have is that the torsion of the bismuth connection that was a 3 form is related to this theta, is related to the Lie form of the metric through the Hodge star operator. And so in fact, what you can prove is that if you are on a surface, so real dimension 4, okay, complex dimension 2, on a Hermitian surface, then the metric, your metric is Bismuth-Keller-like if and only if it is Weismann. Okay, so essentially, these Bismuth-Keller-like matrix coincide with Weismann matrix, okay? So essentially, this means that in dimension 2, we already know what these matrices look like. Actually, compact Weismann surfaces are classified by Belgun, so essentially, we know what these matrices look like. And the point, the crucial point, fact here is that Weismann matrices are Goduchon matrix. So as I was saying, so if you have a Weismann matrix, it's always a Goduchon matrix, but on a surface, Goduchon matrix, if you remember, coincide with pluriclosed matrix. So this is the equation for pluriclosed matrix. And in dimension 2, but this is only true for dimension 2, pluriclosed matrix coincide with Goduchon matrix, okay? And Weismann matrix are Goduchon. So essentially, this implication, Weismann implies this, is trivial, is essentially trivial, okay? But we will have many problems in a higher dimension, as we will see. So, and in fact, let me say that in general, Andrade and Villacampa proved that every Weismann manifold, so in any dimension on any Weismann manifold, the torsion of the bismuth connection is always parallel. So essentially, this other implication, Weismann implies this condition is true in any dimension. Okay. All right. So again, the two-dimensional case is special because, in fact, again, having symmetries implies that we have special matrix. For instance, if you do not look at the whole Kerr-like symmetry. So you don't look at the first Bianchi identity, but you just look at the second part of the Kerr-like definition that was essentially saying that we have some J invariance for the curvature of the bismuth connection. In fact, in this case, on a surface, we can prove that if we have this, then the metric is locally conformally Kähler. Okay, so if you assume that the full Kähler-like condition that was first Bianchi identity, you have a Weismann metric. If you weaken a little bit the assumption and you just ask for this, again, you obtain something. You obtain that your metric is quite good. It's actually a locally conformally Kähler metric. Okay, so essentially the two-dimensional case is kind of understood. Okay, so we know what bismuth Kähler-like manifolds look like. Okay, so they are Weismann surfaces, and in the compact case, they're classified by Belgun. So what about other examples? So again, we have the bismuth flat case, as I said before, of course. If you have that the curvature is 0, you have all the symmetries you want. So of course, they are bismuth Kähler-like. And then with Anna Fino, we showed that we had some characterizations for the existence of bismuth Kähler-like manifolds metrics on almost abelian Lie groups. I mean, we had some explicit examples. But unfortunately, again, we cannot construct new examples using deformations, small deformations of the complex structure, okay? Because this property is not open on the small deformations. But the point, the real remark here is that due to a result of Angel and Ottoman, in fact, this equivalence between Weismann metrics and bismuth Kähler-like metrics cannot be true starting from dimension 3, okay? So because they proved that, in fact, starting from complex dimension 3, if you have a compact Weismann manifold, then you cannot have any pluriclosed metric, okay? So in particular, bismuth Kähler-like manifolds were pluriclosed, okay? So this means that starting from dimension 3, we cannot have bismuth Kähler-like metrics on Weismann manifolds. So you see, we have a very different behavior, okay? So in dimension 2, Weismann and bismuth Kähler-like were essentially the same. But again, this was due to the fact that Weismann metrics were Goduchon. So the implication Weismann implies this was for free, okay? But starting from dimension 3, actually, this is not true, but in fact, you cannot have two different metrics, one Weismann and one satisfying this condition, okay? And this is due to this result of Angel and Ottoman. So the question is clear now, okay? So what are these manifolds, bismuth Kähler-like manifolds in higher dimension, okay? Okay, so now I want to give you this construction with it of bismuth Kähler-like manifolds, and then we will see that actually every bismuth Kähler-like manifold, so BKL, is in fact constructed in this way. So essentially this is the result. So the construction is the following. So start with some three-dimensional Sazakian manifolds, okay, let's say Si. And I will denote with K a compact semi-simple Lie group of rank R, endowed with a B-invariant metric. And then fix a natural number such that if you take L plus S, that is the number of Sazakian manifolds, plus R, the rank, I want this number to be even, okay? And also, I do not want this number to be too large. And then you construct this product, okay? So you take a Euclidean space times the Sazakian manifolds times the Lie group K, and I want this manifold to be, again, even dimensional. We take here the product Riemannian metric on this manifold. And okay, so we take the Euclidean metric, the Sazakian matrix, and the B-invariant metric on the Lie group. And then we construct J in the following way. So just a few notations. So denote with H1, HL, a Levi-Civita parallel frame for the Euclidean space. And then on each Sasaki manifold, we have their Reb vector fields, okay? So we have For each Sasaki manifold, we have one rep vector field. So I will denote these vector fields with H L plus 1 to L plus S. And finally, denote with T a maximal torus of K with this frame, say, again, use with the same letter H, okay? So from L plus S plus 1, and then I would have L plus S plus R that was an even number called 2M, okay? So an almost complex structure, J, is called standard if it satisfies this property. So the distribution spanned by this frame, H1, H2M, so we have the frame for RL, the rep vector fields, and then the torus essentially. So I want this distribution to be spanned by this to be J invariant. And then on each three-dimensional Sasaki manifolds, we have the rep vector field, and then we have this transversal two-dimensional distribution that have a natural complex structure that is essentially induced by the Sasaki structure. And then I want the complex structure we are constructing to coincide with this natural transverse complex structure. And finally, I want J to project to K-invariant complex structure on the remaining part. Okay, so what happens? It happens that, in fact, this complex structure is integrable, and it is compatible with the Riemannian metric in the sense that the Riemannian metric becomes Hermitian. Okay, so this is an Hermitian manifold, first of all. And so what happens is that, in fact, essentially these manifolds are the building blocks of these Bismuth-Keller-like manifolds. Okay, so the result is the following. So if you have a complete simply connected Hermitian manifold, this manifold is pluriclose with parallel bismuth torsion. So if you remember, this means that it is Bismuth-Keller-like. We have the first Bianchi identity. So this manifold has this if and only if it decomposes as a product of Hermitian irreducible factors. So these factors can be either Keller. Of course, you can have Keller factors. So Keller manifolds, as we said, have the Keller symmetries, okay? Keller-like symmetries, okay? So we can always have Keller factors. But then the point is that the non-Keller factors are exactly of this type with the Hermitian structure we described, okay? So just a few words about the proof is that one way of the proof is a computation. So you have essentially to check that these manifolds are with the structure, with the Hermitian structure we described, they are pluriclose with parallel bismuth torsion. So it's a computation. You have to check that the matrix is pluriclose and that the torsion is parallel. So the hard part is the opposite, okay? To prove that if you have a pluriclose metric with parallel bismuth torsion, and in case this metric is non-Keller, it splits, so the manifold splits like this, okay? So, and essentially a key point is that the torsion using this hypothesis, the torsion satisfies the Jacobi identity. So it turns out that the torsion is inducing a Lie bracket on the tangent space, so essentially on the tangent bundle. Okay, so we have a Lie algebra bundle on the tangent space with Lie bracket induced by the torsion. And then you have to check that your complex structure and Arion metric, so that the complex structure, again, is integrable with respect to this new Lie bracket, and that the metric is being invariant with respect to this Lie bracket. And this, thanks to some result of Pitti, gives some root space decomposition of the fiber of this Lie algebra bundle, which in fact turns out to give bismuth parallel decomposition of the tangent bundle. And so once you have this decomposition of the tangent bundle, what you have is that you can show that, in fact, this decomposition will lead to a de Rham decomposition of the manifold, okay? Of course, there are lots of details, but let's say these are the steps. And finally, that you have your de Rham decomposition, you have to understand what are these de Rham factors. And this is essentially done again, using the symmetries of the curvature, because it turns out that every ideal of G with rank at least 2 is necessary bismuth flat. So essentially what happens is that you separate bismuth flat part with the non-bismuth flat part. And I should say that the only non-bismuth flat part is given by the three-dimensional Sasaki manifolds, okay? So that's the only non-bismuth flat part. Everything else is flat. And being flat means that you have a Lie group with a B-invariant metric. This is due to some other results, okay? So these are a little bit just a sketch of the proof. Let me just conclude by saying that actually this result was known already up to dimension 5, because the point is that now that you have this, okay, you have this splitting here. So now you can use the classification, okay, for these Lie groups, okay, for compact simply connected simple Lie groups. And so you can go to low dimension and you can understand what are these manifolds, okay? So for instance, if you have a complete bismuth killer-like manifold that is full, so full means that the universal cover does not have any Kähler-Durand factor, okay? Assume that you don't have anything Kähler, otherwise you would have something Kähler times something of low dimension, okay? So you look at the classification in lower dimension, okay? So just look at the genuine non-Kähler factors. Then if you are in dimension 3, so real dimension 6, then actually you can only have products of two three-dimensional Sasaki manifolds, okay? And this is due to the conditions we had before about the dimensions, okay? So this can be of very high dimension. And again, this factor RL cannot be too large. So you cannot have, for instance, R3 times Sasakian manifold, okay? This would not be Hermitian reducible, okay? So you can just have the product of two three-dimensional Sasaki manifolds. In dimension 4, so the three-dimensional case is due to Yao Zhao Zhang. The cases of dimension 4 and 5 are due to Zhao and Zhang. So in dimension 4, the universal cover is either SU3, which is bismuth flat, or R2 times the Sasakians, to the product of two Sasakian manifolds. And finally, in dimension 5, they proved that they just had spin 5 or SU3 times R2, sorry, or these R times the product of these three Sasakian manifolds. And that's it, okay? So these are the only possibilities due to that. But their result was proven using a coordinate approach, so a completely different approach, okay? But as you see, up to dimension 5, you never have all these three elements. You never have the product of an Euclidean factor, the Sasakian, and then the Lie group. You either have, the Lie group or the Lie group times the Euclidean factor, or Euclidean factors times the Sasakians. Okay, you never have the three ingredients. And in fact, so the first dimension where this happens is dimension 6. Okay, so in fact, dimension 6 is the first dimension where you can really see all these three ingredients. So as a consequence of our theorem, we have that, again, if you have a complete bismuth-Kähler-like manifold of complex dimension 6, with no Kähler-Durand factor in the universal cover, then in fact the universal cover can be just given by these factors. And here you see that you finally have an Euclidean factor, a three-dimensional Sasakian manifolds, and a Lie group, okay? But this is the first dimension where you can really see all these three parts. And so on, of course, you could go in higher dimension. And just to conclude, just to say that, so these very nice symmetries, in fact, are quite restrictive. What we proved, during the proof, what we realized is that having these nice symmetries implies that essentially the curvature is almost always 0. I mean, the Sasaki factors are the only non-bismuth flat components. And in fact, what really happens is that the bismuth Ricci form, so the Ricci form of the bismuth connection completely determines the curvature. Okay, so for instance, if you have a complete simply connected pluriclosed manifold with parallel bismuth torsion, and if the curvature, sorry, the Ricci form is 0 for the bismuth connection, essentially we recover again this result of Zhao and Zhang and Brienza-Fino-Granciarov, that you have either Kähler-Ricci flat manifolds, but the non-Kähler factors are bismuth flat. I mean, if they are bismuth-Ricci flat, they are bismuth flat, actually, okay? Because the bismuth-Ricci form encodes all the informations of the curvature for these manifolds. And, well, bismuth-Ricci flat manifolds are, let's say, very interesting from many points of view, in particular on pluriclosed manifolds. When you have that the Ricci form is 0, these manifolds are called bismuth-Hermitian-Einstein, and they are fixed points of the pluriclosed flow that is, let's say, a non-Kähler analog of the Kähler-Ricci flow. And so what happens is that, again, in the compact case, if you have this condition that the Ricci form is 0, so that the metric is bismuth-Hermitian-Einstein, and you have a bismuth-Kähler-like metric, then you have a compact, it is finally covered, your manifold. So up to a finite cover, you have a compact Kähler-Ricci flat manifold times a compact bismuth flat manifold. So you see, they have a very rigid behavior. But again, just let me say, this is just up to finite cover. Okay, there is an example of Brienza-Fino-Granciarov saying that these manifolds do not have to be a product. Okay, it doesn't mean that your manifold, your compact bismuth-Hermitian-Einstein manifold with parallel bismuth torsion is a product. Okay, but in fact, it seems that this condition, parallel bismuth torsion, is implied by having bismuth-Hermitian-Einstein, so Ricci form being 0. This is true in dimension 2 by Godushon and Ivanov. Apostolov, Barbaro, Listritz showed that there are some possibilities also in dimension 3. There are some rigidities, but it is not known in general. So it is, let's say, so let me say, conclude just saying that it is conjectured that bismuth-Hermitian-Einstein manifolds are bismuth-Kähler-like. Okay, so in case they are bismuth-Kähler-like, they are covered by the result we showed that we proved with Barbaro and Pediconi. Okay, so it seems that maybe this condition is not necessary. Okay, so I can stop here. Thank you.
Thank you, Nicoleta. Very, very, very interesting. Now we are open for questions. If anyone wants to make a question for Nicoleta, please raise your hand and I will allow you to mute. Let me configure this. Okay. Okay, maybe I can start with a question. You know, you have in your say I don't know what is which slide is my, but the main result, the characterization of the construction of the bismuth-Kähler-like manifolds. I think maybe that for that I think that construction is very, very, very interesting and I like it. But maybe you already know that the manifolds with that form you already know that are bismuth-Kähler-like, right? Or where the idea comes to consider. You already have, I mean, you already have examples in this form of bismuth-Kähler-like, and or not?
Yes and no, because, okay, so the problem was that we had examples mainly in low dimensions. So for instance, we knew this result of Yao Zhao Zhang, but you see again, you don't have all the 3 elements, okay? So the examples we had the Euclidean factor times the Sazakians, or the Euclidean factors times the Lie group. So essentially what we knew was that if you take this product, okay, and then you take the Hermitian structure I described reduced to this specific case, we knew that these manifolds were Bismuth-Keller-like. And this was done by Zhao and Zhang, again, for L, not too large again, and three-dimensional Sazakian manifolds. This we knew. We knew that if you take RL times K, this is Bismuth-Keller-like. Okay, so this is something we knew because they are Bismuth flat, essentially. So essentially what we had is somehow we had to put these informations together, okay, to realize that this product was Bismuth-Keller-like, and then prove that in fact all Bismuth-Keller-like manifolds are like this. So somehow, yes, we had some ideas already that these were probably the manifolds, playing the game,
Okay, okay. Now I understand. Maybe you think in combining all the factors and not only R. We will try to prove that is two of them maybe. But it's okay. That one last question because that construction I think is interesting. And another question I have, but this is just a curiosity, but at the beginning of the presentation, there's a result of, let me see, I go here. Yes, that Gauduchon metric always exists
yes,
and is unique, right?
yes,
But
yes.
yes.
Uniqueness, of course, if I assume n greater than 1.
And
Otherwise, I have a Riemann surface of scalar, so I have a lot of Gauduchon metrics, but yeah.
Okay, but my question is, I didn't understand because there is a Gauduchon metric in the conformal class of any Hermitian metric.
Exactly.
So any Gaussian metric is conform. Okay.
Yes, so the idea is this. So you pick an arbitrary Hermitian metric, the one you want, anything. And then you look in the conformal class, so you can multiply your metric with a smooth positive function. Okay, and then you can find in the conformal class one, let's say, a good function so that this new metric you have, let's say function times your initial metric, this is Gauduchon. Because what happens is that essentially this function is in the kernel of some good elliptic operator. It's the adjoint of the Chern Laplacian. So it's essentially everything is reduced to study, let's say, this function, multiplying your metric in such a way that this metric is satisfying this differential equation. And what happens is that this function is in the kernel of this elliptic operator. And then, so you study this kernel. So the proof goes essentially like this. In fact, what happens is that this kernel is one-dimensional. Okay, so that's why you have uniqueness up to positive constant.
Okay. All right, thank you. I got a question from the chat, not the chat in Zoom, but in YouTube. And the question is, were the metrics localized in the 16 classes of gray hair Bella?
Yes, of course, yes. These metrics are in this classification of Greer-Bell. Yes, yeah. I mean, they classified essentially all these special, in the almost complex case, actually, all these special Hermitian metrics, so they appear in the classification. Of course, as soon as you are in the non-Keller setting, you have a lot of special Hermitian metrics. I mean, in this talk we saw a few, and there are actually more, so,
Okay, right. Any more questions? If not, let's thank again Nicoleta. Very interesting talk.
Thank you.
Thank you for accepting our invitation. And as I said to Professor Megan, I hope you can participate in another of our initiatives from ICMAM.
Thank you very much. Thank you again.
Okay, so next talk is by Professor Lino Grama, but it will be in an hour and a half. So you can go to have lunch, come later. You can be here, but there is no interaction for this moment. Thank you to all the participants and see you later. Ok. Oi, Lino, tudo bem? Hum,
Oi, Brian, tudo bem? Tá me ouvindo?
agora sim. Bem-vindo, Lino. Obrigado por participar.
Obrigado, Brian. Obrigado pelo convite.
Ok. I think we
Posso compartilhar
can.
minha tela?
Ah, sim. Vamos fazer um teste melhor primeiro. Mas espera aí que eu tenho que parar de compartilhar. Agora foi. Estamos vendo já.
É, peraí. Posso compartilhar a tela inteira, Brian?
Sim, acho que é
É,
melhor. Perfeito. Pode passar os slides, só para ver?
tá bem, né?
Ah, perfeito, perfeito, perfeito. Ok. Okay, we can start now. It is really a pleasure for me to introduce Professor Lino Grama from Unicam. This session is especially meaningful for me as Lino is my mentor. I'm really happy he accepted our invitation. And he is going to talk about twisted Keller-Einstein metrics on flag varieties. Welcome, Lino. Go ahead whenever you're ready.
Okay, thank you, Brian. Thank you to the organizers, Paola Saavedra and Brian Grajales for organizing this webinar, the web conference. I'm very happy to speak here, and I'm very happy to attend the invitation of Brian. He's my friend for many, many years. And today I will talk about this twisted Keller-Einstein of flag varieties. And this is just here. Okay, this is based on the joint work with my colleague here in the Unicamp is Professor Edward Correa, is also professor here. And it's based on this paper is published the end of the last year. And let's start. Okay, I'll start with the X compact. I just recall general setup. Let's start with the X compact Keller manifold, and we choose in a Keller class, and we fix 1 form beta, and we are looking for a solution, omega, of this following equation. The heat curvature of the metric associated to the omega to be equal to omega plus this described class beta, okay? And this omega, we call this a twisted Keller-Einstein metric, okay? If beta is equal to 0, this is to be the Keller-Einstein metric, just the standard equation of the Einstein equation. Okay, and for the usual funnel varieties, if we start with the Xi to be the first Chern class and take beta is equal to 0, this equation is not always solvable. There's not always solution of this equation, but there is one theorem that exists always a twisted Keller-Einstein metric on the pair X in the prescribed class beta, if beta is case stable, is a case stable, okay? This is analogous to the Keller-Einstein problem. If you consider the case with the classical case when the Xi is the first Chern class and take beta is equal to 0, this is now the famous theorem proved 10 years ago in 2015 by Chen, Donalds, and Sun. And this guy, the three authors, consider this powerful machinery from the K stability to provide this criteria to the funnel manifold to admit these Keller-Einstein matrices. And we have this analogous to this twisted version. Other authors, such Bergman, Buxton, and Johnson, characterize the existence of the twisted Keller-Einstein when we have this class, 1-1 class, given by the first Chern class of line bundle, and the beta to be in a positive 1-1 class. But they use an analog of this delta invariant. This is a very also, to set up this is use a lot of the ingredients, and this delta invariant was originally defined by the Fujita and Odaka. But if you compute this delta invariant, in general, is not an easy task. And actually, even for the usual case, to find the Keller-Einstein matrix in some general setup is not also so easy. And we have also a twisted version for this Keller heat flow. This is a system of the PDE. Here, again, if you start the beta is equal to 0, you arrive in the usual Keller heat flow. But we can also, this is a work by Liu Yang and the Collins Zekihidi. They provide the short time existence. That is actually a geometric flow. And we have this twisted. This is another way to find this twisted Keller matrix by analyzing these stable points of this flow. Again, it is a similar way to the Keller-Einstein matrix usual. Okay. In this talk, in this paper, we will discuss about this invariant solution of the twisted Keller-Einstein equation, but we are considered just a generalized flag variety, so generalized flag manifolds. Okay. And a flag variety, we are considered this homogeneous space, XP, to be the coset space of the complex simple algebraic group, modal, but P, where P is a parabolic subgroup. And now I will state several ingredients of the generalized flag manifolds, and I will describe a lot of geometric components of this space in terms of the Lie theory. Okay, we fix the compact real form of this complex semi-simple Lie group, and in case of the G-invariant Keller-Einstein matrix, we are maintain our main philosophy here, that we are trying to reduce this underlying nonlinear PDE problem. That is just need to solve this nonlinear PDE problem to provide this twisted Keller Einstein. We try to, using this invariant setup and the tools of Lie theory, try to transform the problem in some algebraic problem. Okay? But it still is no trivial. But in the invariant setup, we can change this from some nonlinear PDE to nonlinear algebraic problem. And at the first, we needed to describe this the Picard group of the flag varieties, and we start with this complex semi-simple Lie group, simple Lie group, connect, simple connect, and the complex simple Lie group with simple Lie algebra G. We fix na cartan subálgebra H and a simple root system, and we have this decomposition of the complex Lie algebra in the positive roots, negative roots, and the cartan subalgebra. Okay, and we root space. And we have also the composition of the positive roots and the negative roots. Okay, and this depends on the associated simple set of simple roots. Okay. Now, I denote by this kappa the cartan killing form of the complex simple Lie algebra, and for every positive root alpha, I will there exists an element of the cartan subalgebra we call H alpha in such a way that is just the dual of this covector of this linear functional by the non-generated bilinear form, this cartan killing form, and we can choose two more elements, X alpha, living in the root space associated to alpha, and Y minus alpha, associated in the opposite roots, the negative of alpha, in such a way that the Lie bracket of these two elements will give exactly the H alpha. This is a triple, or this is an SL2 copy of this inside this simple Lie algebra. In fact, it is very well known, this complex simple Lie algebra is just copies of SL2, gluing in some non-trivial way. And we also can define this Borel subalgebra to be this just as a subspace, the sum of the cartan subalgebra and all the root spaces associated to positive roots. I will provide some examples in the matrix in a moment. I will denote by capital B the Borel subgroup. This is the exponential of the subalgebra. And given a parabolic Lie subgroup, we can now assume this is the parabolic for some capital theta, where this capital theta is a subset of the set of simple roots. Okay, and this parabolic subalgebra will be with laws of the generality, this parabolic subalgebra associated to some theta will be this set as a subspace, the sum of all root space associated to this positive roots, plus the cartan subalgebra, plus the sum of the root space associated to some negative roots, not all negative roots, not all negative roots. Okay, we just choose negative roots that lies in this set here because we are choosing some subset of the simple roots, and we take this span of these roots, and we collect all these roots Lies in this span, it's negative, and it consider this root space associated with this guy. Okay, this is in this case we have this all positive roots, cartan subalgebra, and some negative root space. Okay, that depends on this the choice of this set here. And now in the future will be considered we have this inclusion here, this complex torus. This is the Borel subgroup. This always lives inside this parabolic subgroup. This is inside this complex subgroup, okay? Given by this, here the description of these settings. And as I told you, this complex flag variety is just the complex simple Lie group G modeled out by this parabolic subgroup. But will be convenient for us consider another description of this space to be, we consider a compact real form of GC, and we can also describe this flag variety XP as a G space, as now is a real space, G action of the real group. In that way, it will be G over the intersection of G with the parabolic subgroup. Let me put this in a more concrete way, okay? Just, I don't know, have a lot of specialists here, but just to be left to this situation a little bit more concrete. Let me start with this G to be SL5C. This is a complex, simple Lie algebra. Okay, I choose this standard Cartan subalgebra of the diagonal, okay, a matrix. And with this choice, this the set of the positive roots, the root space associated to the positive roots will be exactly the upper triangular matrix, okay? It star here, it blue star is corresponding to the root space, okay? And now I needed to choose this theta. You call this capital theta is a subset of the simple roots. With this choice of the Cartan subalgebra, etc., the root space associated to the simple roots is the next diagonal, okay? You have the principal diagonal, you have the next diagonal, okay? And for the, I choose the set of these three simple roots here. We have this red cycle here, okay? Which flag variety we arrive in this situation, okay? If you take the span of these simple roots, okay, for instance, if I sum this root with this root, you arrive here. If I sum this root with this root, we arrive here, and so on. And then we take the span, which roots, which positive roots we can produce with just these three simple roots, and take the negative, okay? It's an exercise. You can check this. We will arrive at this upper, this all roots here, and then consider the diagonal. We take the opposite. And in this case, this green, I'm not sure if you, okay, it's green. Believe me, this is all these spaces here. We in green, in the below the principal diagonal, will be this. The sum of a root space associated to some negative roots. Just to be clear, let me back here. Okay, at this p theta, n plus some h, some n of theta minus. Okay, in that example, the n plus is the green, sorry, is the blue. The h is the diagonal in the red, and the n minus theta is the green above. On this theta is the some roots I make some circle, head side. Okay. Okay. This is the h, the Cartan subalgebra. This is the positive roots, and this is a choice of the capital theta, and this is the root span, the negative root spanned by theta. Okay. And when I mod out SL5 over this parabolic subalgebra, I arrive at this homogeneous space. This is CP4, okay? this is the SU5 over this SU4 times U1. This SU5 is the maximal compact subgroup inside SL5. Okay, and this is the realization as a real homogeneous space, but this is also complex because that is a SL5C over the parabolic. And you can think this SLC over this parabolic is expanded by these red dots here. And what will survive after the quotient will be just these black dots. Okay? And then this is very usual to people use this a lot. And then this is each here is a two-dimensional 1, 2, 3, 4. And then we have 4 complex dimension or 8 real dimension. This is actually the tangent space at the origin of this homogeneous space, the complex tangent space. Okay. One more example, I can start with the same Lie algebra, but now I can choose different simple roots. Okay. For each choice of simple roots, we can arrive at a different homogeneous space. Okay. Let me check here. Now I choose these 2 simple roots. Okay. And we can check this with these 2 simple roots. I produce this another simple root. This is the sum of this. I make some standard choice here. Okay, that not go inside this. And when I take the negative of this, I arrive to this green dots. And now I have the parabolic subgroup is determined by these red stars. And what survive is this black dots here, black star here. Okay, and okay, we can check this. This is this homogeneous space, SU5 over U3 times U1 times U1. And then this is identified also with the projectivization of the tangent bundle of the CP4. Okay, CP4 have a complex dimension 4. The tangent bundle of CP4 have the complex dimension 8. But when you take the projectivization, you kill 1 dimension. Okay, we have 1, 2, 3, 4, 5, 6, 7 dimension. Okay, is a H less 1. Okay, and this is of course is a different flag rights. Okay, and it depends on the choice you made at the beginning for the choice of the capital theta. You can arrive in different homogeneous space. Okay. But the main idea here is you can understand lots of the complex geometry, from symplectic geometry, from Riemann geometry, just understand this theoretical phenomena, and you can understand this. The main ingredient is understanding this capital theta. Okay, I will provide more details now. Okay, a little bit more theoretical ingredients here. For every simple root alpha, okay, I can just make a normalization on this vector H alpha. Recall this H alpha just the dual vector by this pairing, by the Cartan-Killing form, okay? Because for Cartan-Killing form, I can make the pair between this vector and the roots. Roots is a linear functional, okay? This is just, this H alpha is just a dual to the functional alpha, is a simple root. And this H hat is just a normalization of this. And I can define now this the fundamental weights. Is also linear functional, and this is just the dual of this vector. Okay, in that sense. Okay, when I apply this omega alpha in the H hat beta, I have the delta Kronecker. Okay, depends on alpha and beta. Okay, this is again this lies in the dual of the Cartan subalgebra. This is a linear function. And we can using these fundamental weights, I have the set of the integral dominant weights is the Z model expanded by this linear functional. And now we have some, this is a very, very nice theorem by Assad and Bizas. This characterizes the G invariant Keller form on flag varieties in terms of the Keller potential, and describe explicitly the Keller potential of any Keller form, or G invariant Keller form on flag variety. Okay, we see if you start with omega, one form invariant, closed invariant on the flag variety. We have this pullback by the group G is given by this expression, square root of -1, del del bar of phi, where phi is given explicitly in terms of the representation here associated to this flag variety. I take the sum over the complementary simple roots. I mean, I take this capital theta, this is the set used to define the flag variety, and take the complementary, okay? And then I make the sum over this log of this function, G on V plus omega alpha, and this is ingredient comes from this representation theory. Okay, this is the eigenvector vector on this, associated to this representation with eigenvector weight omega. And G of V is the induced action of G in the fundamental representation. This is, okay, if you sit down and write down, you can produce this, okay? And conversely, if you have a function defined as above, I can define a one-one invariant real, closed real form on the flag variety. And to characterize this G invariant Keller form, I just need to ask if this coefficient C alpha to be positive for all complementary roots. Okay, this is this is very, very nice because I can work with this Keller potential. Okay, explicitly. Just describe in terms of the Lie theory associated to this flag variety. Lie theory and the representation theory of Lie algebras and the etc. Okay, now let's consider this this principal associated principal P bundle. This is just the homogeneous vibration, and we choose now open cover of the flag varieties in terms of this Check cocycles, and given a fundamental weight on the capital lambda plus, we are consider the induced character by this weight, such that the derivative of this map at the origin will be exactly this omega alpha. And we use this character. This is a homomorphism from the parabolic subgroup to C star. And we can put a structure on C of P space in such a way that the action of P over Z will be exactly the action of the character times Z. And this is what I need to produce a P space, or a line bundle on the flag variety, okay? We can associate holomorphic line bundle. I call this O alpha 1. It's just to be this C times C minus omega twisted by P. This is just the associated bundle. And then we can describe this in terms of the Check cocycles. This is just the transition function of the line bundle. Okay, because in this case the line bundle it can characterize just by the functions in the intersection take values in the fiber, the C star, and this Check cocycles is just this composition of this transition function psi ij with the character we are producing at the beginning. Okay, and again, we can just describe these line bundles using lit2. Okay? Now we denote by nabla the chair connection on this line bundle, and with curvature of this connection f nabla. And we consider this G invariant form capital omega, such that this form satisfies this the following. Okay, this is just a normalization of the curvature, the two form of curvature, the curvature form. Okay, let's consider this to be just a normalization, square root of -1 over 2 pi. And we have this line bundle. The first chart class is just the curvature class. Okay, this we have this fact. This is very well known for another context, but here we just repeat this. But we would like to emphasize this construction are involved just the tools of the representation theory. Okay. And now we consider the Picard group, the group of line bundles over this complex manifold. And here we can repeat this construction for every simple root. Okay, and then you can produce, of course, the simple root, not every simple root, but the surviving simple root. That I have start with the sigma of set of simple roots. We choose some theta, and they take the complementary root. Okay, and then for each simple root in this set, in this complement, I can make this produce one line bundle. Okay, and then for each line bundle, the curvature is the first chart class, and we can now describe this Picard group. Let XP be the complex flag variety associated to some parabolic subgroup P theta. And then we have this following description. This Picard group of XP is the Z model spanned by this omega alpha, where alpha, I take alpha inside this set, in the simple roots, the complementary of simple roots with respect to the set theta. Just one remark, that is, if I take any G invariant Riemann-Geometric on the flag variety, I can denote by this curve H, this space of real two forms on this flag variety. And we can also denote by this set of the closed invariant one form. That is a very nice result of the Takeuchi. That the set of the closed G invariant real one form described by Bissat in Biswas in Nazat are harmonic with respect to any G invariant Riemann-Geometric. Okay, that is another phenomenon like this in another different settings, but there's some geometric objects there's some property with respect of any G invariant Riemann-Geometric. Okay, in this case, this is harmonic with respect to any G invariant Riemann-Geometric. People call this a key harmonic true form. Okay, and then we use this very soon. We have the Keller cone. The Keller cone of a complex flag variety is just this. We take this all haze. This is just a positive real number times this vector. You can think this like a basis of some vector space and just take a race. Okay, just take this Keller cone. This is because just for every Keller structure will be described with positive linear combination with positive coefficients in terms of these fundamental forms. And this is just agree with this result of Assad Biswas because you just need to pick some positive coefficient. And we have also this kind of the dual, a kind of the cone of curves. Okay, we have this set we call cone of curves. It's denoted by NE of a flag varieties. Is generated by these rational curves. That is for each complementary simple root, we associate one P1. Okay, this is the simple way to see this. And recall you have the triple H alpha, X alpha, and the Y minus alpha. This triple will generate SL2C, and then the compact real form is a SU2, is a three-sphere. And we have, when you take the projection, if after some careful analysis, you can understand this like a Hopf vibration. And inside the flag manifold, you have a lot of these P1s. Okay? And these have these rational curves, this P1 alpha. For each alpha, you have this SU2, and this projected in SU2 in these spheres, P1. Okay? But you need a lot of careful here, but there's a lot of identification. Okay? But this we will use also, and for each simple root, complementary simple root, we have some spheres inside this our flag variety. In more, and I can say more. These is spheres, this P1, are generator of the pi2 of this flag variety. Okay? And now I can describe this the canonical line bundle. Okay, will be just this tensor of line bundles. Okay, this O alpha L alpha just mean a tensor O1 L alpha times, and which is this L alpha is just this pairing here. This is just in a covector. This is the linear functional, and this is a vector. This is just a pairing. Okay, and this delta P is a number appears a lot in the representation theory, is the sum of these positive roots. Okay, or in this case we remove this root spanned by theta. Okay, again I can describe this canonical line bundle. It appears a lot in the algebraic geometry, in this complex geometry, and I can describe this in terms of these ingredients. Okay, and if you consider an invariant Keller metric, rho 0, we can describe this rho 0 in terms of this base here. Okay, just consider this formula here is a very useful, very useful. This terms is the sum of this positive root, and we need to pair this with this H alpha when we take the sum over this complementary root. This is this is important. Here is always be positive, and this is a kind of the base of the Keller form. Okay, and we can make some computations, and in this case, the first shared class will be given by this class normalized by 2 pi. Okay, and we have a unique G-invariant representative on each cohomology class, and it's followed that this this rho determined by this exactly these coefficients. This is the way to produce the invariant Keller-Einstein metric. Okay, that this is a unique Keller-Einstein metric in the flag manifolds. Okay, in the flag varieties. Okay. And this is the way to describe this. And this form here, rho naught, with these coefficients in this first shared class, is the unique Keller-Einstein metric. This solves this Einstein equation. Okay, this is the very classical result by Matsushima. Okay. And for unities of the G-invariant representative on the first shared class, given any G-invariant Keller metric, we have this, the which is constant. And we can also compute the curvature, the scalar curvature of this metric, and the scalar curvature is constant of the scalar metric. And okay, this is our setup. Okay, these are our ingredients from the elite theory. Now I start to state our results on this twisted Keller-Einstein method. Okay, our first result is if I take an aligning bundle and I prescribe on beta on a cohomology class to form one form, then with the input that exists a unique G invariant Keller metric omega on the Flag manifold XP, satisfying this twisted Keller-Einstein equation. If and only if I can, the beta is solve this inequality. Okay, this of course this inequality is not trivial. You need to check a lot of things, but I can inside the set of invariant one form, I can draw like hyperplanes inside this scalar cone. I know precisely which place I can pick one beta to solve this, to guarantee that there is a Keller metric solving this twisted Keller-Einstein equation. This is a if and only if I can precisely describe this region inside the Keller cone where there is solution of this twisted Keller-Einstein equation. But you need just to understand this inequality here. Okay, this is I can understand this like a pairing between these two cohomology class with this two cycle, two sphere. Okay, this is our first contribution. Okay, maybe I don't know how much time I have, Brian. 10 minutes or 15 minutes?
20 more minutes. But
20 more minutes. Okay.
maybe we can leave some time for questions.
Okay. I just said maybe I can back this at the end if you, but I just the idea is a very careful analysis of this Picard group. I needed to work with this some cohomology class and produce this analyzing this representation theory ingredients here. We can make some candidates to line bundles to produce this result. Okay, and after we have this candidate, we need to check this system of inequality, okay, to produce this what you want. And the opposite, we needed to make the reverse. We needed to define some Keller form in the Keller cone, and then check if it will satisfy the twisted Keller-Einstein equation. Okay, and okay. By now we have the Keller cone, and we can now make some several inequalities. We can think like hyperplanes inside the cone, and we need the region when I can pick one form beta to solve the twisted Keller-Einstein equation. Okay, and some consequences if you take in a Keller class and a 1-1 form invariant exactly in this set, in this cohomology C1 of P less this Keller class, then this is always solvable. I can guarantee that exists a unique G invariant Keller metric that is twisted Keller-Einstein by bit, is a twisted by bit. Okay, this is a consequence just to consider beta inside this set, and you can make some computations and solve for this. Let me just put some examples here. Flag varieties with the Picard number 2. This is very concrete, okay? because of the now we are cone is a two generator, it's a cone, it's a real cone in the plane. Okay, it's a very complete. And the Picard number 2 are parameterized by flag manifolds when I choose the capital theta in such a way that the complementary simple roots sigma less theta, that is just two elements, alpha 1 and alpha 2 simple roots. Okay. And one way to see this is you take the Dink diagram and then just mark two roots. That's the two roots will survive, okay, after you take the complement. And then this is a number here is a delta, is the delta I defined before. This is a half sum of this positive roots, but I changed the base root to put in some fundamental weights here. This is a these are very well known in the literature. You can find these in the books from the representation theory. There's no secret here. But for instance, this homogeneous space, that is a Picard number 2. Okay, for all L. This is very nice. It's for families. Okay, this family also, that is Picard number 2. But look here. If you choose different, if you make some different choice, the geometry will change here. Okay, this is very drastic. Okay? Depends on the roots you choose. Again, all these three homogeneous spaces are homogeneous space of SL2L, but it depends on the choice of the simple roots. You can arrive at a very different homogeneous space. This is a family of the symplectic SPL, again, okay. This is some exceptional Lie group E6. That is flag varieties from E6, okay. And this is very more dramatically the same manifold, but depends. You need it. Actually, in the literature, these two last flag manifolds appear some marks in the U4 because the U4 inside the E6 they can take the different subalgebras inside. But this is a very nice phenomenon, okay. And then for all these manifolds, for all flag manifolds with Picard number 2, okay, we can reduce a system of two system of inequalities, okay, and I can solve the twisted Keller-Einstein equation, H omega is equal to omega plus beta, if and only if the class beta satisfies these two inequalities, okay. The integral of beta over this P1 associated to alpha is less than 2 pi times L1, and the integral of beta over P1 now over alpha 2 is less than 2 pi L2, okay? And in this case, I can also give the precisely what is the Keller form is in terms of the Keller cone. Now you can think this, you have this, the Keller cone is a ray. I don't know if you see me, but you have in the plane, you have a cone, okay? And now you have two lines, and then you can, inside the cone, prescribe precisely the region where if every beta inside this region will produce a solution of the twisted Keller-Einstein equation. And these lines essentially are given by this L1 and L2. This is really complete, okay? It's in plane. You can draw this picture. It's a very nice, okay? And for this class of flag manifolds or flag varieties, you can precisely describe a region inside the Keller cone is always solvable, this problem. And another example here is a projectivization of the tangent bundle of the complex projective plane. This is an example I gave before. This is a family of flag varieties given by this homogeneous space, SUN plus 2, UN times 1 times 1. I will be a little bit fast here because, okay, this is a very nice, this is a positivization of tangent bundle of CPN plus 1. This is a very nice remark by his group. And now I work in this Lie algebra SL n plus 2. And the set we are considering is just this. If I put in the diagonal, I just will consider these two last roots, consecutive roots. Okay, this is a final remark. Sigma less theta, you just expand by two simple roots. And if you make some ordering in diagonal, I just take the two last elements. Okay, and in this case, the rank of the H2 of this flag variety is 2. Okay. And now I can compute this representation to the ingredients, and again, I will arrive on two systems, in the system of the inequalities, and I can solve this problem of the twist Keller-Einstein if and only if my class beta satisfies these two inequalities. Okay. Again, I can do some similar picture here, but inside the Keller cone, for this family is also two-dimensional, but I can put some hyperplanes inside the cone and take exactly this region. Okay. And just some consequence of our result, I can consider the Keller cone of any compact Keller manifold. And for any Keller class inside the cone, I can define the greatest heat lower bound as this set. I take the set of the real numbers, R, such that exists a Keller form omega, normalized here, such that the heat curvature of this Keller metric is bigger or equal to R times the class omega. Okay, and I take the supremum of this set of the real. Okay, this was studied by this geometric analysis researchers, but the first for Tian. In the case of the Keller class, is the first Chern class of the manifold, and Zakehidi proved that this, if you take this interval closed in 0 and open in this number, if you consider just the class to be the first Chern class, this is the maximum interval for the when we can apply the continuity method to solve the Keller-Einstein equation. Okay, so this number is useful for geometric analysis to people apply very hard analysis technique in this method to solve PDEs in the Keller-Einstein equation. Okay, but recently Song and Young used this estimate to prove the existence of the conical Keller-Einstein on some Fano manifolds. This is you can use this greatest heat lower bound in context of geometric analysis. But again, if you take these papers, to produce this number is not so easy. Okay, just some few examples of explicit computation are known. And for instance, the people know this invariant explicitly for P2 and the blow up at one point. This is Zakehidi, provided by Zakehidi. And we know for all toric Fano manifolds is a very recent produced by Lee. But we can use our results to prove the following explicit expression for this greatest heat lower bound for any Keller class. Note that this is the example are just consider the class of the first Chern class. And okay, we are working on flag varieties. And this is our second remark. We can provide this number just in terms of the combinatorics of the Lie theory and the representation theory. Okay. This is known for any complex flag manifolds of in any Keller class. Okay, this is a very interesting because we can now produce for a huge family of examples. And now, given this Keller class, Zhang recently proved this inequality using this greatest fit lower bound. But Berman and Bergson also provide another inequality, but this regarding this canonical bundle power n of this compact Keller manifold. Okay, but the first inequality was also known by Flegg-Wright, by another author called Snow. And using our technique, we can put both inequalities in one, because these inequalities are proved separate and that are, at least are not related. But using our technique, we can also put these two inequalities in this sequence, and we can also make some estimates for the middle. Okay, this is a new also. Okay, people don't know this before. And that is a very nice to remark. This is essentially used tools from a lead theory. Okay, that is it. I just to the papers I quote here. Okay, and this is a very recent topic. There is a lot of papers are quite new. Okay, and okay, this is a very accessible subject, very nice. Okay, and that's it. Thank you.
Thank you so much, Lino, for your talk. Thank you for be here. And if someone would like to ask, feel free to, it's the moment, feel free. Someone has question or would like to?
I have one.
Okay.
Thank you, Lino, for your talk. Maybe I want to know if is there any example where the integrals of the beta can explicitly be computed or at least bounded.
Yes, this is actually this is just a notation. You can actually this is for this is a little bit tricky because if beta is in the same class of the alpha, this is just the pairing in topology. Okay, just probably some number, integer number. But beta can be to combine. Okay, and then explicitly we don't know on the direction. Just try to find the region inside the Keller cone where for sure we provide a solution. Okay. But this is not in general too easy to compute explicitly. The integral, okay? This is the integral, and integral is not in general, but I need some makes the estimation. But if I know inside the Keller cone precisely when this inequality will hold. This is for sure. Okay, because I have the explicit basis of the Picard group, and I know how to express in terms of basis each form beta. But this is a very, very explicit. At least in this case of rank 2. Okay, in the bigger dimension, you make some intersection of a lot of hyperplanes inside one quantum. But it's possible also to try to imagine the region, but the main thing is inside this region, if I pick beta inside the region, I can always solve the problem.
Okay, thank you.
Okay.
And another question is maybe what happens if you consider beta, for example, a small perturbation of beta outside the gene variant forms? Maybe the case when beta is not gene variant, you can say something. Yeah.
No, I don't know. I don't know. But okay, now we escape of this invariant world, right? Now we are in the real life. Okay, very hard is a hard analysis. Okay, but we can use this invariant R psi because people from PDE like this continuation method to solve PDE, and now we have some chance to try to apply this technique. This is a guarantee we can produce a solution, but I don't know if it very short time deformation, but we need to investigate. I don't know. I don't know.
Thank you.
Thank you. Thank you so much. Someone has another question. Okay, I
Okay,
will
let me
say.
stop here. Okay, thank you for
Thank
inviting
you.
me.
Thank you so
Thank
much,
you. Thank
Lino.
you.
I appreciate to be here to accept the invitation. And thank you so much.
Okay, thank you.
Bye bye. Thank you.
Bye bye.
So the next talk is given by Francesca.
Hi.
Hi. Hello.
Hi.
How are you?
I'm fine. And you?
Fine, fine. Thank you so much for being here.
Oh, can I share the screen before?
Yes, yes, yes. I will try to give you this access. Let me do that. You can't share. It is.
Okay, I try.
No, let me.
Do you see my screen?
Yes, yes, yes. I can see the screen. Yes.
Okay, 1 minute since I have this bar.
No, it's perfect.
1 minute.
You can see
Okay.
it. Yes. So
I don't 1 minute. 1 minute since I'm not sure that in full screen it is good.
I can see. I can see.
Yeah. Yes. Sorry.
The presentation. So let me introduce you. Thank you so much. Thank you, Francesca. I am the next speaker for us, and I appreciate to be here you to accept the invitation. And Francesca is right now working in the Escuela Superiore Meridionale, and she will give a talk about the EDM's mass and potential theory. So it is, thank you, and it's you, it's all for you.
Okay, thanks to organizer for this invitation. It is very pleasure to give this talk to this big conference. Oh, okay. The outline of this talk is the following. We will introduce the notion of asymptotically flat manifolds and ADM mass. After, we will present alternative proofs of the positive mass inequality and the Riemannian-Penrose inequality. At the end, if we have time, we will show some geometric inequalities involving the ADM mass, the capacity, and the perimeter of the boundary. So we now introduce the asymptotically flat manifolds, a smooth connected Riemannian manifold with or without boundary of dimension n greater or equal to 3 is called asymptotically flat of order tau greater than 0 if there exists a closely bounded subset K such that n minus k is a finite joint union of open set called ends. Every end is diffeomorphic to Rn minus a closed ball with the center at the origin via a diffeomorphism phi called asymptotically flat chart, such that the pushword of the metric G by phi is equal to the Euclidean metric plus a 0,2 symmetric tensor of coefficient sigma KL, which are big O2 of the norm of x to the minus tau, with the expression with the expression big O2 of the norm of x to the minus tau. We are describing the behavior at infinity of sigma KL, its first partial derivative and its second partial derivative in this way. In these slides, we have some example. Here we have an example of a asymptotically flat manifold with a single end. Here with two ends, and here with the three ends, 1, 2, and 3. Two key aspects are contained in the definition of asymptotically flat manifold. One is topological. The manifold may have a quite complicated topology, but this is all concentrated in bounded and closed subset of the manifold. And the other concerns the behavior of the metric at infinity. For the definition of asymptotically flat manifold is not uniform in literature. For smooth metrics, the completeness or the number of the ends or the rate of decay of the metric at infinity, or also assumption involving the scalar curvature are some of the points where the definition may differ. Physically, one expects asymptotically flat trimanifold arise among Riemannian hypersurfaces of spacetimes modeling isolated gravitational systems. Where with the spacetime we mean a quadridimensional time-oriented Lorentzian manifold satisfying the Einstein equation. In the Einstein equation, the spacetime says to matter how to move, and the matter says to the spacetime how to curve. With the term isolated gravitational system, we mean a finite set of gravitational objects, for example, stars or black holes, in an otherwise empty universe. The most famous solution to the Einstein equation with the T identical 0, so the vacuum Einstein equation, is the Schwarzschild spacetime, which models a static black hole of mass m. The T-slice of the Schwarzschild spacetime of mass m are totally geodesic Riemannian hypersurfaces. They coincide with the same Riemannian manifold called Schwarzschild manifold of mass m, which is given in this way. The Schwarzschild manifolds of mass m are asymptotically flat with a single end. The metric is conformal to the Euclidean metric via an appropriate power of an harmonic function. So the scalar curvature of the Schwarzschild manifolds is identically 0. However, we have a dependence of the geometry of the geometry on the sign of the parameter m. For m negative, the metric degenerates on the boundary. For m equal to 0, the Schwarzschild manifold can be smoothly extended across the origin, and the Riemannian manifold so obtained is isometric to the Euclidean space. For M positive, the Schwarzschild manifold extends smoothly to all Rn minus the origin, and the Riemannian manifold so obtained is asymptotically flat with two ends. From now on, for M positive with the Schwarzschild manifold of mass M, we mean the complete Riemannian manifold with boundary given in this way. And this sphere, remember, it is totally geodesic. In particular, it is minimal. It is most important is the only sphere minimal in this manifold. For each end of an asymptotically flat manifold, we can define the ADM mass. Now we see the definition of ADM mass. We consider an asymptotically flat manifold Mg of order tau greater than n-2/2, such that the scalar curvature is integrable or non-negative. For each end mi of the manifold, we define the ADM mass via this limit by using an asymptotically flat chart on the end mi. Finally, we define the total mass of the manifold Mg, which is the sum of the ADM masses of all ends of the manifold. Bartnik and Kruschel provided independently that the ADM mass of each end is well defined in the sense that this limit exists. More precisely, this limit is finite if the scalar curvature is integrable, and it is equal to plus infinity if R is non-negative, the scalar curvature is non-negative, but it is not integrable. Moreover, the ADM mass is a geometric invariant in the sense that this limit does not depend on particular asymptotically flat chart chosen to compute it. We return to physics to explain why the term mass is appropriate in this setting. In 1960, Arno Dresner-Misner made a detailed study of isolated gravitational systems. They adopted the Hamiltonian viewpoint. This means that they choose a space a Riemannian hypersurface as initial dataset and write Einstein equation as evolutional equation for this initial data. They discovered a conserved quantity, and this quantity is the limit that we have seen before. Moreover, for the Schwarzschild manifold of mass m, this limit is equal to the parameter m up to a constant. But we remember that the Schwarzschild spacetime models for the physics models static black hole with mass m. For these two reasons, they concluded that this conserved quantity represents the total mass of the isolated systems. A famous theorem involving the ADM mass is the positive mass theorem. The theorem says that if Mg be a three-dimensional Riemannian manifold such that Mg is complete. Mg is asymptotically flat with a single end and order tau greater than n minus 2 over 2, and the scalar curvature is non-negative, then the eigenmass is non-negative. This inequality is called the positive mass inequality. Moreover, the equality holds if and only if Mg is symmetric to the Euclidean space. The positive mass theorem can be considered a purely, or the Riemannian positive mass theorem can be considered a purely geometric result, inspired by the physical expectation that in an isolated system, a non-negative mass density implies a non-negative total mass. Some different approaches and tools have been used to prove the positive mass theorem. Shea Yao used minimal surfaces with a spin manifold. Locamp proved positive mass theorem by non-existence theorem for positive scalar curvature matrix, Wisken and Mann via weak inverse mean curvature flow, Lee via Ricci flow, and Bray, Casar, Curie, and Stern by using harmonic function with the linear growth. By joint work with Agostiniani and Mazzieri, we obtained an alternative proof of the positive mass inequality via monotonicity formula that holds along the regular level set of an appropriate harmonic function which is related to the minimal positive green function with the pole. The idea of the proof is the following. We consider the function u equal to 1 minus 4 pi GO, where GO is the minimal positive green function for the Laplacian operator with pole at some point O of the manifold M. Since we are working asymptotically flat manifold, GO exists and vanishes at infinity. By using the function u, we define the function f in this way. With the star, I mean the regular. Since here we are defining the function f for every t in 0 plus infinity, but not all. A priori, we don't know that all t in 0 plus infinity are regular level set of u. So with the star, I mean that I take the regular part of this level set of u. And the function f is well defined. Now, if the topology of M is sufficiently simple, and then we will see what I mean with this expression. We have that if st are values in 0 plus infinity, such that s is less than t, and 1 minus 1 over s and 1 minus 1 over t are regular level set of u, then f evaluated in s is less or equal to f evaluated in t. F is a non-decreasing on the open set of t on the set of open set of the values t in 0 plus infinity, such that 1 minus 1 over t is a regular radius for u. How we prove this fact, and it is the following. So in this open set given by M minus the union of the pole and the set of critical points of view, the set of the critical points of view is the set of the points such that the norm of gradient u is equal to 0. In this open set, we can consider this smooth vector field X, which satisfy these two important properties. The first is that for every t in 0 plus infinity, such that 1 minus 1 over t is a regular value of u, ft is equal to the integral on this regular level set of u of gx, the normal. Point at infinity, so gradient u over the norm of gradient u. Another property of x is that the divergence of x can be expressed in terms of the geometry of the portion of the regular level set passing at the points passing at the point where the divergence is computed in this way. Here, NT means a non-negative term. For the inequality, the expression of this non-negative term is not important. For the rigidity, yes. But now we are now we are speaking only of the positive mass inequality, so it is not important the real expression of these terms, but only the sign of these terms. Afterward, we show that ft minus fs is greater or equal to this integral, the divergence of x, on this open set, u greater than 1 minus 1 over s and less than 1 minus 1 over t. We observe that, that this inequality is an equality if this open set does not contain critical points of U by the divergence theorem. If this open set contains critical points of U, we can show this inequality by using an appropriate family of cutoff function. Later, we apply the Coarea formula and the Sartre theorem to obtain this equality. Again, NT means non-negative terms. Finally, we use the assumption that the scalar curvature is non-negative. Okay, now with the simple topology, I mean that the second integer homology group of M is equal to 0. If we know this topological assumption and U is and we have that U is harmonic, we can say by using maximum principle that every regular level set of U is connected. So the Gauss-Bonnet theorem guarantees that this difference is greater or equal to 0. So we can see here that this term is non-negative, R is non-negative, and then we have these non-negative terms. So we can conclude that that Ft is greater or equal to Fs. Now, by a work of Bray, Casars, Curie, and Stern, it is sufficient to show the positive mass inequality in the class of Riemannian manifolds satisfy the assumptions of the positive mass theorem and also the following two properties. The first, M is diffeomorphic to R3, and it is a topological simplification. And second, there exists a distinguished asymptotically flat chart phi such that the pushword of the metric G by phi is the Schwarzschild metric, and the parameter obviously is equal to the ADM mass of the manifold M. And it is a simplification of the metric at infinity. The topological simplification guarantees that the function f is non-decreasing on the open set of value t in 0 plus infinity, such that 1 minus 1 over t is a regular value of u. Consequently, we can compare the limit of ft for t tends to plus infinity with the limit of ft for t tends to 0. Now, this limit is equal to 0 by using the behavior of the green function near the pole. And this limit is equal to a pi radian mass, and this is a consequence of the fact that in this distinguished asymptotically flat chart, such that the push word of the metric G is the Schwarzschild metric, we have a better behavior of the function u near infinity, which is given by this formula. In this way, we obtain that radial mass is greater or equal to 0, so the positive mass inequality. Two remarks. The first is that by the same work of Brekhazar Curie Stern, the positive mass inequality also holds in asymptotically flat manifold with multiple ends. The positive mass rigidity is true by the work of Shane and Yao, in which they showed the rigidity part by using only the positive mass inequality, and not the way they obtain this inequality. Another remark is the following. Currently, we know how to show that the limit of ft for t tends to plus infinity is less than or equal to a pi radian mass, even without the simplification of the metric to infinity. Indeed, one can note that we can write ft as a sum of mt plus qt, where mt and qt are given in this way. The limit of qt for t tends to plus infinity is equal to 0, and to obtain this limit is enough to know the classical behavior of u near infinity in a generic asymptotically flat chart. Since when we know this behavior, we can compute the behavior of this quantity and of the area of this regular level set of u. The limit of of mt for t tends to plus infinity is more complicated, more difficult, and to compute it, we inspired to the work of Whiskey and Heyman on inverse mean curvature flow. In these slides, I want to remark that the completeness of Mg, the non-negativity of the scalar curvature, the existence of the minimal positive green function with pole that vanishes at infinity, and controlling the topology implies that ft is non-negative for every t, such that 1 minus 1 over t is a regular value of u. Now, if we know also that the minimal positive the norm of the gradient of GO tends to 0 at infinity. From this non-negativity, we can obtain this volume comparison. So the volume of this sub-level set of U is greater or equal to the volume of the Euclidean ball of dimension 3. And this volume comparison leads to a more geometric proof of the positive mass inequality. Indeed, if we assume that again Mg is complete, asymptotically flat with a single end, and order tau greater than n minus 2 over 2, The scalar curvature is non-negative, M is isomorphic R3, that is the simplification, the topological simplification, and we have also simplification of the metric at infinity. These points 1, 2, and 3 and 4 implies that we have the previous volume comparison. Now, since we have this distinguished asymptotically flat chart such that the pushword of the metric G is the Schwarzschild metric. We know the better behavior of U near infinity in this asymptotically flat chart. And by using this behavior, we can compute this expansion. So joining these two information, we obtain this inequality, and we obtain for pi the idea mass plus a term that tends to 0 at infinity, tends to 0 when t tends to plus infinity. So passing to the limit for t tends to plus infinity, we obtain again the positive mass inequality. So we have seen two proof of the positive mass inequality. In both proofs, we use the topological simplification. But we have seen that in the first proof we can remove the simplification of the metric at infinity, but I think that it is not true for the second proof. The advantage of the second proof lies only on the fact that it is more geometric, in the sense that in this case we obtain the positive mass theorem in some sense to comparing by a volume comparison. Okay, now I want to pass to another famous theorem involving the ADM mass. In this case, we consider a manifold with boundary, which is the Riemannian-Peroz inequality. In this case, we consider Mg be a three-dimensional Riemannian manifold with boundary, such that Mg is complete, asymptotically flat with a single end, and the order now is equal to 1. The scalar curvature is non-negative, and the boundary in this case is compact connected, and it is the unique closed minimal surface in Mg. Then the AD mass is greater or equal to the square root of the area of boundary over 16 pi, and the equality holds if and only if Mg is symmetric to a Schwarzschild manifold of mass greater than 0. Again, the Riemannian-Peroz inequality can be considered a pure geometric inequality, motivated by the Peroz conjecture. The Peroz conjecture states that the total energy of an isolated gravitational system is at least equal to the total mass of the black holes that are present, assuming some energy condition. In 21, the Riemannian-Peroz inequality with a single black hole. With a single black hole, we mean that the boundary is connected. Was proved by Wisken and Manen via the weak inverse mean curvature flow. In the same year, the Riemannian-Peroz inequality with multiple black holes. So in this case, the boundary may have multiple connected components. Was obtained by Bray via a conformal flow of metrics. Now, by joint work with Agostiniani, Mantegazza, and Mazzieri, we obtained a proof of the inequality via a monotonicity formula that holds along the level set of appropriate p harmonic functions. Some points of this proof are inspired by the work of Wisken and Hendelmannen. Following our approach, we cannot conclude the part concerning the rigidity in the statement. However, our proof does not require any knowledge of geometric flows. Okay, in this case, we consider the weak solution of the following problem. By using this function u, we define the function fpt for every t such that alpha pt is a regular value of u, where alpha pt is given by this formula. This formula. In this formula appears Cp, and Cp is related to the P capacity of the boundary, and we recall the definition. It is the infimum of the set of the integral of m of norm of gradient v to the p for all v in C infinity. Which are equal to 1 on the boundary. A motivation behind the construction of the function of fp is the following. We can define the function of Fp by using this identity. Now the function Fp satisfies this equation. When p tends to 1, we obtain the solution of the inverse mean curvature flow. So the idea is to construct the function fp such that when we we evaluate this function at the value e to the power t minus 2, we obtain a quantity such that when p tends to 1, we obtain up to a constant the Hawking mass of the level set of phi, and phi is a solution of the inverse mean curvature flow. And it is known that that the Hawking mass is non-decreasing along the regular level, along the level set of a smooth solution of the inverse mean curvature flow. Okay, now we have seen the motivation. Now I wanted to give we continue the proof in which we use the function fp. More precisely, fp is non-decreasing when it is well defined, and similar to the proof of positive mass theorem. In this case we find a smooth vector field x p outside the set of critical points of u, such that again fpt is equal to the integral on this regular level set of u of gx phi gradient u of norm of gradient u, and the divergence of x p can be written in terms of the geometry of the portion of regular level set passing at the points where the divergence is computed in this way, where n and t means a non-negative terms again. Then we obtain that fpt minus fps is greater or equal to the integral of this open set of the divergence of x times the characteristic function of m minus the critical set of u. Again, if this open set does not contain critical points of u, this inequality is an equality by the divergence theorem. if this open set contains critical points of U, we obtain this inequality by using an appropriate family of Kaptov function. Then we apply the coarea formula. We don't the coarea formula and we don't consider the non-negative terms. The difference with respect to the proof of the positive mass theorem is the following. In the proof of positive mass theorem, positive mass inequality, we consider harmonic function. Harmonic functions are smooth, so we can apply the SAR theorem. Now, for the p-harmonic function, we know that in general the p-harmonic functions are only C1 on all manifold C1, and for this reason we cannot apply the SAR theorem. So in this case, the set of the critical values of U could have positive Lebesgue measure, and so the Gauss-Bonnet theorem is not sufficient to establish the non-negative of the non-negativity of this term. So in order to obtain the monotonicity, we consider the solution U epsilon capital T of the following perturbated problem, where T is sufficiently large regular values of U. Now we know that for this solution, these solutions are smooth. So for this solution, we can apply the SAR theorem. And also this function approximates smoothly the p-harmonic function U on the compact subset contained in M capital T minus the set of critical points of view when epsilon tends to 0. Now, by using this function, we construct new function fp epsilon that converge to fp when epsilon tends to 0, and also they are almost monotone in the sense that when the error tends to 0, we obtain the monotonicity. At the end, we can say that the limit of fp t for t tends to plus infinity is greater or equal to the limit of ft in tp. This tp is a value in 0 plus infinity such that, 1 minute, sorry, such that alpha p tp is equal to 0. So we obtained the boundary. Now the boundary is minimal. We use this fact to obtain this inequality, and the limit of t for t tends to plus infinity is less or equal to a pi daddy mass. And in order to obtain this inequality, we use a result of work Benatti, Fogagnolo, and Mazzieri, in which they obtained asymptotic expansion of U in a generic asymptotically flat chart, and this asymptotic expansion is given in this way. Then the Riemann-Amperes inequality follows by semi p to 1, since the limit for p tends to 1 of the p capacitor boundary is greater or equal to the area of the boundary. And here we are using a result in the paper of Fogagnolo and Mazzieri. Now, Benatti, Fogagnolo, and Mazzieri show with the same previous inequality, and also so they obtain the Riemann-Amperes inequality when they send P to 1 under a weaker assumption of the metric at infinity. Hirsch, Miao, and Tam found other monotone quantities associated with the same harmonic function. As a consequence, they obtained an equality related now that the mass, the peak capacity, and the Wilmore energy of the boundary. By letting P to 1, they obtain that radiant mass is greater or equal to the Hawking mass of the boundary, under the assumption that the boundary is only area out and minimizing. They don't require the fact that the boundary is minimal and it is the only minimal closed surface in mg. So it is more general. Since I have time, I wanted to also treat other geometric inequalities. Now the setting is very similar as before. Again, we consider a three-dimensional Riemannian manifold MG with a compact and connected boundary. Again, we assume that MG is complete, asymptotically flat with a single end. Now the order is greater than n minus 2 over 2. The scalar curvature is non-negative, and the topology is sufficiently simple. We have seen before that the function fp that we have seen before are constant if and only if mg is symmetric to the Euclidean space of dimension 3 minus a ball. Monotone functions which are constant if and only if mg is symmetric to a Schwarzschild manifold of mass m greater to 0 were constructed by Miao and myself in the case of harmonic functions, and by Xia, Zhu, and Mazurowski and Yao for any p greater than 1 and less than 3. Usually the consequence of these monotone quantities are geometric inequalities involving the radiant mass, the capacity, the perimeter, the capacity of the boundary, the perimeter of the boundary. But in this case, they are sharp in the sense that if the equality also, we can say that the manifold is the Schwarzschild manifold. This is a big difference. Some examples is the following. In this paper, we obtain this inequality. Again, this inequality is an if the equality also, we can say that the Schwarzschild, we can say that the manifold is the Schwarzschild manifold of mass equal to the capacity. A consequence of this inequality can be an alternative proof of the positive mass again of the positive mass inequality. Since if we consider m equal to n minus a geodesic ball with the center R, now Miao observed this behavior about the capacity of this boundary of the integral of the mean curvature normal gradient u, and integral on the ball of normal gradient u square. And so if we send r to 0, we obtain the positive mass inequality. Another inequality is the following. If there exists alpha in this open set, such that the mean curvature of the boundary is related of normal for gradient u, in this way, we can say that the capacity is less or equal to the square root of the area of boundary over 16 pi or the radiant mass. And again, if the quality holds for one of these inequality, we can say that Mg is isometric to a Schwarzschild manifold of positive mass. One consequence of this inequality is the black hole uniqueness theorem for substatic manifold. In fact, if Mg emits a solution to this problem, in a joint work with Agostiniani and Mazzieri, we obtain this inequality. So the capacity is greater or equal to the square root of area boundary over 60 pi. But before we have seen that the capacity is less than the square root of area boundary over 60 pi. So in this case, we have the equality, and if we have the equality, we can say that the manifold is the Schwarzschild manifold. But here it is important that we are requiring the topological assumption. Assumption. Future direction is the following: to study p harmonic functions, to obtain geometric inequality in setting with the different lower bounds on the scalar curvature. Okay, it is all, and thanks for your attention.
Thank you so much. Thank you so much, Francesca. It's a beautiful talk. It was a beautiful talk. Someone has would like to ask. It's the time to do that. If someone has questions. Okay, I would like to ask you. You told about the Wilmore conjecture, but the only thing that I know about the Wilmore conjecture is given by Godard. This no inequality, but this proof related to minimal, yes, minimal submanifolds. It connects with your where you talk, or is different results about
No,
because
I don't use the only Wilbur inequality that I use is a very standard. So if you use in some point I say that the limit of ft for t tends to plus infinity is less than a pi Dadian mass.
okay,
Without the assumption the metric at infinity, in the sense that we don't require that the metric there exists a distinguished asymptotical effect chart such that the pushword of the metric is the Schwarzschild metric. And in order to obtain this inequality, one ingredient is the Wilmore inequality, in the sense that we say the Wilmore functional for this level set is always greater or equal to 16 pi. So I don't use the Wilmore conjecture. So I use the classical inequality that was proved by Wilmore. So it is very classical. So I don't use,
okay,
fortunately, I don't use Wilmore conjecture here. It's very standard.
okay, okay,
So
okay. Thank you.
in the sense that there is the Wilmore functional, but
Mhm.
not it is not related to the, I think, to the Wilmore conjecture. Obviously, what I can say that if we in some sense we have mass, um, you need to think that there are some surface that satisfy the reverse Wilmore inequality. So the integral of h square is called less than or equal to 16 pi. So the presence of the mass, you obtain the reverse inequality. So usually it is not true that the Wilmore is greater or equal to 16 pi for this manifold. So also you can investigate also the presence of the mass, how change when you analyze also manifold with the fixed genius. So since the Wilmore conjecture says that if you consider genius greater or equal to 1, you can say that the Wilmore function is greater or equal. Okay, there is a right constant that usually I don't remember, since it depends if you divide the mean curvature for 2 or 4 or for 4 or not, and you obtain the Clifford torus. But here no, here we analyzed this inequality, so it is different with the
different assumptions also. Okay, thank you so much, Francesca, for your talk, and thank you to be here, accept the invitation. Thank you so much.
No, thank you for the invitation. Thank you.
Thank you. Bye. So the next talk will be given by Mariel. So hi.
Hello.
Hello. How are you? How are you?
Good, you?
Fine, fine. I am happy about your talk will be about flows, which is something that I am trying to understand better. Geometric flows is also my area.
Okay, good.
Can you share
Yes.
your screen, please, and we will see if anything works.
Yeah, let me try to share. And let me go into full screen. Can you see well, or?
Yes. I can see well the presentation. And could you show me another?
Yes.
Okay. Yes. It works, in fact. Okay. So we will continue our conference with Mariel. Thank you so much for accept our invitations. You are working right now in the Pontificia Universidad Católica de Chile, and she will give us the talk, which has a title given by geometric flows and some applications. So thank you. It's your time.
Thank you.
Thank you so much.
Thank you very much for the invitation. And actually for today, instead of a research talk, I plan more a survey talk to introduce the area, because I know that usually in these online talks, there's a very diverse audience and not everyone is very familiar with geometric flows. So most of my talk is actually not my work, but someone is trying to enter, but just general facts about geometric flows and how this can be used as a tool for other things. And at the end, if there is time, I'll talk a little bit about one of my results, but if not, at least I hope you get an idea why this is an interesting area, and there are many open questions here that you can work on still. And let's see now if I will start with concepts that probably everyone knows, but usually when I give these talks about geometric flows for general audiences, it turns out that in differential geometry, if you work in certain particular area, sometimes some of the concepts are a little bit different, or like the ones that people are more familiar with are not exactly the same. So I decided to start with things that probably everyone has heard before, but at least we can agree on some of the basic things. And please stop me if I'm not being clear about something, or if I'm going too fast, because when I cannot see the faces of everyone, I tend to go a little bit faster than I should. I can be I can run a little bit through the talks in that case. So the basic thing is that for me, a flow is gonna be the idea of changing an object in time, and that object that you change is gonna depend on the kind of flow that you're working on, and I'm gonna be more precise about this, but what I want you to think about now, that when I talk about flows, I mean changing some object, and that object is gonna be given by a context that I'm gonna give you in a few more minutes. And the word geometric is that the law of change, the speed of the flow, is gonna be given by a geometric quantity. And when I say this is an example that I gave for other talks, but I guess this is maybe more familiar for people here. For instance, when you have when you blow a soap bubble, and this starts moving, this moves, changes shape, and it eventually takes a final shape that is, in most cases, round. Some people can do many things that are much more complicated than that, but this process of changing is what I understand as a flow. In that case, the type of object that I described before is going to be a surface, and the law of change is something that minimizes the tension energy of the surface in that particular example. I'm going to be more precise about this in a few minutes. And the word geometric, I guess, for people here knows what it means, but I guess geometric for me it means that it's something that is independent of parametrization, basically independent of the way I describe the manifold. And in my talk, most things are going to be extrinsic. So in some sense, what it means that it's independent of how I parameterize my surface in the previous example. So the standard geometric objects that I'm going to be talking today about are length, volume, tangents, normals, and curvatures. The most important quantity today is going to be curvatures, and I'm going to discuss the concept of curvature that I'm going to use briefly, but I hope that when we get to the examples, it's going to be more clear. And here's where I guess the most difference happens when I talk to different audiences. Historically, usually we have extrinsic geometry and intrinsic geometry. When we talk about extrinsic geometry, the first thing that most people is familiar with is the curvature of a curve. That the geometric representation of that is, if you take a curve and you take the circle that better adjusts to this curve, the curvature what describes is 1 over the radius of that circle there. And then you can generalize this to any dimension. Well, here's a computation of the curvature, but what is important here really is two things in that formula that I wrote down there. One thing is that it's a quantity that involves second derivatives of the parametrization of the curve. And the second important thing is that this quantity is something that it doesn't depend on how I parameterize the curve. This is independent of parametrization. And there are a few more things that we will need to discuss in a minute. I see a lot of people coming in. Maybe I think I started a couple of minutes earlier, and that's why everyone is coming in right now. So if I say something that you need me to repeat, I can do that. So as I was saying, so the important thing about for me in this formula that I wrote down there that you have to keep in mind is that this is something that involves second derivatives of the curve and is something that is independent on how I parameterize the quantity that is there. Okay, in general, for me, the principal curvatures are gonna be the eigenvalues of the shape operator. If you're not super familiar with extrinsic curvatures, usually in surfaces, the way that one usually starts describing this is that, okay, over a surface, I can draw many curves and I can compute the curvatures of all those curves. The maximum one and the minimum one are called the principal curvatures. If you want to go in higher dimensions, in reality, what you need to observe is that when you take the differential of the normal, think about codimension 1 for now. Of course, if you have higher codimension, you have many normal vectors, but if you're codimension 1, you basically have one with different possible directions, but just one. And if you take the differential of that, one can see that the eigenvalues of that matrix are independent of parametrization, because basically changes of parametrization correspond to a change of basis on how you take that derivative. So the eigenvalues is something that is independent of the basis in which I describe the matrix. And those eigenvalues are called the principal curvatures. And these are objects that are independent of parametrizations, and functions on that are objects that are independent of parametrization. So in general, when we talk about extrinsic geometry in this talk, we're always going to be talking about principal curvatures. I will be choosing certain functions that are interesting about principal curvatures. The mean curvature for me, and this I wrote because I know that not for everyone this is a definition, is going to be the trace of the shape operator. Is going to be the sum of all the principal curvatures. In the literature, often they take the average, they divide by something. For me, it's just going to be the sum. It's not a big change in many things, but there are some constants that are going to be changing depending on whether you take the average or not. For me, it's just the sum. And in the intrinsic approach is something that in general I'm not going to discuss much. I'm just going to say a few words, because if I'm talking about geometric flows, I cannot ignore completely the intrinsic approach. So I'm not going to enter into detail how you define things. But I want to say in this context, for me, all manifolds are going to be Riemannian. I'm always going to be on a Riemannian ambient manifold. And in most cases, I'm going to be in Euclidean space, actually. But if I'm not, I'm always thinking that it's Riemannian. And I'm not going to describe what are the different types of curvatures here, but what I want to keep in mind is that because it's Riemannian, we can endow the manifold with a metric. And for me, then the curvatures are objects that depend on second derivatives of the metric, different combinations of that, and that are independent of parametrization. So as I said, I'm going to mostly be talking in this talk about extrinsic geometry, but some of the things have parallels in intrinsic geometry, and usually the parallels are like that. The mean curvature, although of course is not the same and it's not really completely related, it's going to be related to the Ricci curvature. There is some sort of trace in the case of intrinsic geometry. So there are many parallels in between intrinsic and extrinsic geometry in the world of geometric flows. But for me today, most examples today, because they're easier to draw, are going to be extrinsic. Because also my research is more related to extrinsic flows than intrinsic flows. Okay, so these two worlds are of course related to each other, and there are also some of the things that I'm not going to touch on today, but if someone wants to discuss more or ask me more about that, there's also some couplings between extrinsic flows and intrinsic flows. No, I'm not going to go into that, but there are many interesting directions of research there. And now finally I'm going to enter into the topic of geometric flows, and hopefully I can a little bit go into what was discussed in the previous talk about the Penrose inequality. I want to touch on that idea also by the end of this idea of geometric flows. Okay, so a geometric flow is going to be the evolution of a curve of a surface for me, in general of a manifold, that the speed depends on a geometric quantity, on a curvature usually. I'm going to explain why I want that. The evolution, the geometric flows, again, can be intrinsic or extrinsic. My flows are going to be mostly extrinsic today. And that means that what I'm going to be evolving in this talk is the embedding of a certain manifold into another. So here I wrote it the other way around, I guess. In the extrinsic case, usually we have an embedding of a manifold into another, and what we're going to be changing is that embedding in time. While in the intrinsic case, usually what you see is evolutions of metrics. It's the metric that is changing in time, and that's the class of objects. For me today, as I said, they're mostly going to be extrinsic, so what I'm going to be changing is how I embed one object into another. And something that is going to be underlying in all the all the talk here, that is something that is important in the extrinsic case, but not in the intrinsic case, is that all my manifolds today that I'm going to be evolving, all my surfaces are going to be hypersurfaces, are going to be codimension 1, because many of the things that I'm going to say today are simpler or even only true in the case of codimension 1. When you have higher codimension, you see many more phenomena, and maybe I can say a few words about that after discussing the codimension 1 case. But somehow I'm always going to forget, because for me, everything today that is the simpler case to discuss is going to be codimension 1. So it's going to be a hypersurface of dimension n in Rn plus 1 usually. So you can have that in mind. And one other thing in this world that is important is that the tools that we use are usually related to partial differential equations. So we need to have a structure for the PDE that allow us to actually do the evolution and use known results. And that means in most cases that we're going to have a PDE that, at least in a weak sense, is going to be parabolic. Usually the fact that it's parabolic is not entirely true. There's some degeneration from the fact that you can reparameterize and obtain the same object. So in some sense, they're degenerate parabolic. They're not exactly parabolic, but somehow you can use the geometric structure to go around the fact of that degeneration and understand why is there degenerate. Something that I'm gonna do that I didn't do is open the chat on the site in case someone wants to ask something, because I just realized that I'm not seeing that. But I think there's no questions yet. Okay. And what I want to start with is actually the simplest example, and that is the curve shortening flow. And for that, I wanted to share with you. Let me see if I can share that. Let me see. I wanna see if I can share my browser with you. Screens. This is what I want to share now. Let's see if you can see this. This is actually something that you can find online. This is the web, the address there, and you can draw your favorite curve here, whatever you like. And this is gonna show you how the evolution looks in time. This is a curve in R2. And this is curve shortening flow. So what I'm doing here, or what you're seeing there, is a video of a curve that in every point the speed is proportional to the curvature and is moving in the normal direction. And maybe the curve that I draw is a little bit big, so it's taking some time. But if you see the curve during the evolution is becoming rounder and rounder, and is actually decreasing area. This is a natural thing, in fact. Is something that is related to the evolution equation that I'm choosing here, because actually the curve shortening flow is the curve that decreases area in the fastest direction, and in particular it decreases area, the enclosed area. So actually one expects this flow to shrink, and if you see it disappeared in finite time relatively fast. I'm gonna draw one more curve to say a few things about how that happens. If you see, I drew a curve there. Too fast. Let me draw another curve, more wiggly, so I have a bit more time here. Let me pause the flow. If you see here, in these points, the curve is convex, and in these points, the curve is not convex. So I don't know if you can see my arrow there, or if can you see the arrow that I'm pointing with, or no?
Yes, I can see the curve. I can see.
But you cannot see the arrow of the cursor of the mouse. You cannot see that.
Yes, no, yes, I can see also
Okay.
the mouse. Yes, it is.
Okay, great. So in these points, the normal vector, the curvature is gonna be positive and it's gonna be pointing this direction, while in these concave parts, the curve is gonna be pushing out. So one can see that the curve is trying to become more convex in time, and for any curve that is reasonable and you draw here, this actually happens. If you pause at some point, you're gonna see that the curve is convex. And even more here in this, you can ask to preserve the area, and the curve is becoming more and more circular. And actually this is a result in the case of curve shortening flow, that it doesn't matter with which curve you start, as long as it doesn't have self-intersections, the curve is gonna become convex in finite time, and it's gonna shrink to a round point. And the round point means that when I preserve the area, this is gonna become basically a circle of that fixed area that I'm preserving. And let me see if I can go back now to the talk. So here you can actually play more with this and do more things. Let me maybe say a few more things, given that I don't want to share. But if for instance now I draw another curve inside, this is going to be preserved. This is also a consequence of this being a parabolic equation, that if I have two curves that compare, then they're going to keep comparing while they evolve. They're not going to touch. If they didn't touch to start with, they're not going to touch later. And there are many other results that actually you can see if you play a little bit with this application here. It's a nice tool to actually show the curve shortening flow. Let me see if I can go back and share the presentation. Let me. Okay. So this is the more basic. I don't know if I'm sharing. Share. Sorry, I should not. I don't know if I cannot see now the presentation. Let me see. You're still seeing the
Yes, I see right now. No, the presentation, no, the program, the app,
yeah.
the curve.
I don't know. Let me maybe stop share and share again. Okay. I don't know what happened. Let me try again this. Can you see it now?
Yes, I can see right now the presentation.
Perfect. Okay, so this is the simplest case of a geometric flow, of an extrinsic geometric flow. And there are a few features that you already saw there in what I showed you before. And maybe the more interesting one is that actually the evolution only exists for a finite time. So in general, you're gonna have that that the evolution here exists for a finite time. And one classical example, easy to compute, that usually when I have a board I do compute it because it's very easy to see, is the case of a circle, where you have that all the curvatures are exactly the same. Well, I mean, of a sphere or a circle, that in this example that you have only one curvature that is the same at every point. And in that case, the evolution stays circular for every time, and you can compute exactly what the evolution is. And here in this example, you see exactly for how long the evolution exists. You see that there's a capital T there that determines the time of evolution. And that capital T, you can compute it exactly in this example in terms of the initial area of the enclosed area of the curve. So all these evolutions are going to exist for finite time. And in the case of curves, we know a bit more that actually they're gonna become round, and they're gonna become a point in finite time. So this was proved by a combination of works of Gage, Hamilton, and Grayson. Gage, Hamilton showed that if you start with something convex, then you have that this converges to a point, and that point after rescaling looks like a circle. And then Grayson showed that it doesn't matter how bad the initial curve is, then it's going to become convex in finite time. So this was around 86, I think. And well, it was kind of a big hope for what was going to come with the other geometric flows. This was kind of the beginning of this era of geometric flows. but quickly then you can try to go into higher dimensions, and the most natural generalization of this flow is the mean curvature flow, where you again have codimension 1, and now the speed is given by the mean curvature, so by the sum of the principal curvatures. And then I also have a video that I wanted to share with you. Let's see if I managed to do it better this time. Let me see. So I think that's a video of mean curvature flow. And then you see that you have some surface there that at this point exactly, there's a singularity happening and it's not becoming a point. So I think this is one of the first examples that was worked out that in fact shows that if you go to higher dimensions, even one more dimension, you have other types of singularities, not only point singularities, but you can have more complicated phenomena in what kind of singular behavior you see in this video. Actually, what tries to do is sort of resolve the singularities, and I don't know why it's showing that after that, but let me go back. Sorry. Let me. Sorry about that. The problems of using the web. So in that case, most of the research in what was to come was to try to understand when do you have singularities or what kind of singularities you may have. The example there again is the example of a sphere that again converges to a point. So you can also have that. You can also have the same type of phenomena that you had for curves. But the question is what other things one can see. Okay, so there's a picture of two different types of singularity. A result by Husken in the mid 80s show that in fact if you start with something convex, that again remains convex and converges to a point, like in the case of a curve. But then you have the dumbbell example, that is the one that I show you the video of, that you have other types of singularities. And in that case, if you rescale there at the neck, what you see in general is like a cylinder. But you can see other things. You can have other types of singularities there. And the conjecture at the time was that all the singularities in this case should be generically points or neck type singularities. But this is not always true. This is only a generic result, which means that if you have an initial surface, you can always perturb it into something that has that kind of behavior, but you have examples where something worse things can happen, which means that in fact this is kind of a difficult problem. And even today, in a series of works has showed that this is true when you're working with surfaces in R3, but even if you go one dimension higher, it's not known. It's not exactly known what all the singularities are. If you have some additional assumptions, you can say things, but in general, you don't know what are all the possible singularities. Okay, so this is one of the main research directions even today. Maybe at the end I'm gonna be able to say a few things about that part, but if not, and I should be looking at the time, I leave it for you to ask or like to research for yourself what is known in these cases. Okay. I wanted to mention just to end, because usually when we talk about Ricci flows, I mean to end with examples, when we talk about Ricci flow with geometric flows, I should mention Ricci flow because it was one of the big promoters of the area. The Ricci flow was created or was first proposed by Richard Hamilton at the beginning of the 80s, trying to prove the Poincaré conjecture, but it became very, very popular in like 2005 or something around that time, when Perelman actually succeeded to prove the Poincaré conjecture using the Ricci flow. And the history previous to that was that there were many results in mean curvature flow that were kind of parallel to Ricci flow, because there are many things in the structure of the equation that are similar. So even if it's not true and there's no real parallel, many things that you see in mean curvature flow, you expect to see in Ricci flow in one dimension less. So for instance, everything that is known for mean curvature flow of curves is expected to happen something similar for Ricci flow in 2D. The case of where you have the uniformization where you know the uniformization theorem, so you have more information and it's kind of a simpler case. And Ricci flow in dimension 3 should be a little bit like mean curvature flow in dimension 2, but it's not true that everything is the same. There are many parallels, but it's not exactly the same. Okay, so this is an intrinsic flow, and it's again like the primary example of an intrinsic flow. And if you want to think about general intrinsic flows, maybe you should know a little bit about Ricci flow, I think. So again, it's a parabolic PDE with singularities in finite time, and the classification of singularities is one of the big problems in the area. Okay, so I said everything the other way around, but I think I already mentioned all these facts. I don't want to go into details in the Ricci flow because I guess I want to focus my attention mostly on, as I said, extrinsic flows, where I can show you a few more things. And I want to show you an application of the curve shortening flow that is related to the previous talk, and then I want to say a few words about the previous talk and other things without doing the computations. So something that I want to recall that probably many of you know is that when you have a curve on the plane, then the enclosed area is something that you can compute in terms of the curve that bounds that area. That is that integral there. And now I'm going to assume that I have a curve that is evolving by curve shortening flow. And I want to see how the area evolves. In that case, this is very particular to 2 dimensions that you can compute this, because you can compute the total curvature of any closed curve that is embedded. And a more or less direct computation that requires a little bit of work, but not a lot, shows that the evolution of the area is, and there's a typo here, there's a minus missing in front of the 2. You should say minus 2 pi. That is this minus here that I forgot to write. So as I told you before, if you compute you can compute exactly the evolution of the area. So you can see that the area becomes 0 after A0, the initial area, minus 2 pi times t. So the final time is given by the initial area divided by 2 pi. This is something very particular about 2 dimensions, that we can do this sort of precise computation. And I want to compute now the evolution of the isoperimetric ratio of a curve that is evolving by curve shortening flow. So if you do the computation, here I try to put some of the details, but this is a precise computation, the first line that you see here. And then you can use what's the word? The inequality here, I'm forgetting the word. The Sobolev inequality here to compute this. This is again something that you can compute exactly. And you arrive to this formula over here. So something that you can see here just from this formula is that if L squared divided by 4 ever becomes smaller than minus 4 pi, then this ratio is going to keep decreasing. So the moment that L squared divided by A becomes less than minus 4 pi, then this is going to stay less than minus 4, stay less than 4 pi, and it's going to keep decreasing. Something that I mentioned when I show you that picture that I drew in the evolution is that the curve converges to a circle. So that convergence is actually proven to be very strong. You converge at any order that you want. So and something that happens with L squared divided by A is that it's a quantity scaling invariant. So when you rescale the quantity, you obtain exactly the same. So something that you know is that when L squared divided by A, you evolve the curve up to the final time, this quantity is going to converge to the ratio, the isoperimetric ratio of a circle. And this is something that you can compute explicitly. In the case of a circle, L is 2 pi r, so this is going to be 2 pi r squared divided by pi r squared. The r doesn't matter because it's something that is independent scaling. And this is actually exactly 4 pi. So in the limit, this has to be 4 pi, which means that it cannot be strictly smaller than 4 pi. And that actually tells you from that analysis that L squared divided by A is something that is always bigger than 4 pi. And this is exactly what is known as the isoperimetric inequality. So you can use curve shortening flow to prove the isoperimetric inequality. Of course, there are many proofs of the isoperimetric inequality, and this is not a new result, but it's kind of a nice, simpler proof. Simple, maybe quote unquote, because of course, to show that every curve evolves to a circle is not so simple. But once you know what the limit behavior or the possible limit behavior of the flow is, then you can actually prove the isoperimetric inequality. And that's where I want to connect with the previous talk, because in fact, you can use one of the important applications of geometric flows is that you can use them to prove different geometric inequalities. And I wanted to show you a couple of examples today. One example is the isoperimetric inequality in bigger dimensions. This can be proved using powers of the mean curvature. The proof only works for things that are mean convex with positive mean curvature, and this is a paper by Felix Schulze in 2008. And the difficulty, and the reason why I chose to show you the other proof is because in the other case, I told you what the limiting behavior is. I told you that this is going to approach a circle. So one thing that you have to know in general is what are you going to approach? What is going to be your limiting object for your isoperimetric quantity? And because in these examples, you may have singularities. So in the previous one, in the example of the curve, I knew that I didn't have any singularities. So I knew that I had a limit and everything was going to be nice. So one difficulty in the general case is going to be how you go through the singularities. So what happens, for instance, with the dumbbell example, when the dumbbell breaks down? How do I know that I preserve the inequality? Other example is the one that you saw in the previous talk. That is the one that is related to the positive mass theorem or to the Penrose inequality. In geometric terms, this can be translated into this inequality. This inequality has been proved using inverse mean curvature flow. And I have also, I want to say a word maybe about inverse mean curvature flow after I've shown you these examples. And there are two cases where it has been proved. There's a proof by Huisken-Ilmanen, that was the one that was mentioned before. And in that case, the single, I mean, you also have to have the condition that the mean curvature is positive, and you have one additional condition that your initial surface has to be what they call outward minimizing. So you have a global restriction on what kind of things can you use. There's another proof that is the same proof that was done by Wan and Lee in 2009. And in that case, they need the surface to be star-shaped. And the reason why they need the surface to be star-shaped is because that case is similar to the case of the curve that I showed you before. It's something that doesn't have any singularities in finite time and that is known to converge to a sphere. So these are always using the same principle. You take your scaling invariant quantity, that in this case is going to be area to the 1/2 divided by h, by integral of h, and you're going to study the evolution of that, or the other way around, and show that this is actually something that in the limit you know what the value is, You saw a little bit of that in the previous talk. And you're going to have to be careful that either to prove that you don't have any singularities, or that when you have a singularity, you can continue your evolution in a way that the inequality is still preserved. The paper of Van and Leaf you see is 8 years later than Ilman and Husken, so you wonder why they would want to prove the same result so many years later with the same idea. And the fact is that this inequality falls into a class of much bigger family of inequalities that are usually known as the core mass inequalities, that are these ones. Here, the integral of sigma k refers sigma. If you take the principal curvatures, these come as eigenvalues of the shape operator, as I said earlier. And then if you take if you take the coefficients of I'm forgetting the word in English at the moment, but when you compute the eigenvalues and you take how you call that in English? I forgot the word now. If you take the polynomial to compute the eigenvalues, then the coefficients of that equation is something that you can write in terms of the principal curvatures. And those coefficients are usually called sigma k's, and this correspond to sums of k distinct eigenvalues and all the possible combinations of that, and those are the sigma k's. So these are objects that define a parabolic equation if you put another restriction on the sign of these polynomials, and that restriction is usually what we say that these surfaces are K-convex. It's a family for which the equation that is defined is actually a geometric flow that is parabolic. And then we can actually use all these tools of PDEs and have comparison, and then we can do a program similar to the one before. And this has been studied by several authors before, but I guess the classical reference is Urbas and Gerhard, that they studied this family of flows and show that when you start with something that is star-shaped, that is a condition that is preserved, so you remain star-shaped for all times, and then you converge to a sphere. Another video that I wanted to show you, now I'm a bit scared because, I don't control YouTube so well, but let me try anyway. Anyway, to do it is, I wanted to show you in these examples how the evolution looks like in the case of inverse mean curvature flow. In this more general case, it's more singular in general, so it's more difficult to show. Let me see if I can do that. So I wanted to show you the dumbbell example in the case of inverse mean curvature flow. And if you see, the behavior is very different than in the case of mean curvature flow, because it's something that expands. And actually, in this example, you can also compute explicitly what let me pause it maybe somewhere in the middle. Is different than mean curvature flow in the sense that these are flows that are expanding instead of contracting. So if you compute the evolution of a sphere, the sphere is going to expand, it's going to increase the enclosed area. The limiting behavior is expected again to be a sphere, and that's why we can compute what this inequality finishes. Basically, it finishes like a sphere as before. But the singular behavior is quite different than in the other cases. So the things that you expect to see in this when you do singularity analysis are quite different than in the case of mean curvature flow. And then, okay, so the difficult, I just want to say in general that, again, in geometric flows, I guess one of the main topics is to try to understand how singularities are, but they're very dependent on the family of flows that you're studying. And contracting flows have very different behavior than expanding flows, and usually the conditions that you need to prove convergence in both cases are slightly different. Okay, let me see if I can go back to the presentation again. I don't know if there are any questions. I feel like I've been talking a lot, but I don't know if you have any questions. So maybe it's a good moment now that I'm trying to see how I reshare to pause and ask if you have any questions so far. Okay, Francesca.
Yes, can I ask, these results, the ambient spaces are tree? Or no, sorry, are n, or could have
It's
some
Rn.
of...
This is
Ah.
Rn, so sigma k, in general, you have it defined up to n, right? So the biggest k that you can choose is n. But in the case, for instance, if you want to put k equal to n, then you need to be convex. Actually, this is only true if the surfaces are convex.
Okay, thank you.
Yeah, being k convex, maybe for people that are more expert on this, means that sigma j is positive for j between 1 and k. And in the case of, so going back to the inverse mean curvature flow, your sigma 1 convex, so means that H is positive. And in the case of inverse mean curvature flow, the weak inverse mean curvature flow, what happens is that you go to the boundary of that cone. So if you wanted to generalize this result for a bigger class, probably the type of singularities that would appear, or what we expect the singularities that appear, is that sigma k becomes 0 at some point. In the case of inverse mean curvature flow, the singular behavior is associated to H becoming 0. Here, the associated flow would have sigma k equal to 0 at the singular time. This is kind of a conjecture; it's not completely proved, but this is the conjecture in this case. Is there any other question? Okay, so just maybe quickly mention that one open question in this case that I'm interested in and that I'm kind of working on at this time is trying to generalize this for something that does have singularities and trying to understand exactly this, exactly when can you continue the flow through singular times that could happen in this case. But because it's very fully nonlinear, it's not so simple. Okay, so just to quickly mention, as I said before, like what popularized geometric flows is the Ricci flow. So I cannot not mention the Poincaré conjecture among the applications. As I said, I don't want to go into details of this. There are many talks that you can find online about this because this was a very popular topic like 20 years ago, but I would say even 10 years ago was still a very popular topic. And in that case, the Poincaré conjecture basically says that if you're simply connected, a three manifold that is simply connected, then it has to be a sphere. And the full geometrization conjecture would give you a classification of three manifolds, a full classification of three manifolds. All this was proved using Ricci flow. And again, maybe the more difficult fact in this proof was to show that certain singularities didn't happen actually for the flow. And I'm gonna say a few words more about this later, but basically when you have a singular time in any geometric flow, usually you can classify them in terms of how fast that happens. When they're slow, let's say, we say that are type 1. This is kind of the natural speed of the flow. And then in the case of mean curvature flow, that corresponds to shrinking solitons that you expect, as I said before, in many cases to be just spheres and cylinders. Or it could happen faster. That is what is called a singularity type 2, in which case these are modeled after translating solutions. I think I'm going to have time to say a few words about this at the end. And in Ricci flow is the same. I mean, you could have fast or slow forming singularities. It was conjectured that all of them were shrinking type, let's say, like spheres and cylinders would be the corresponding thing in mean curvature flow. But it was hard to rule out certain kinds of translating that were not translating in this case, but like the equivalent of translating. And that is basically what Perelman managed to rule out with a lot of work. It was not very simple, but that was enough to prove first the Poincaré conjecture and building on that a full geometrization conjecture. Topological results are not exclusive to intrinsic flows. For mean curvature flow, even you can have some classification results, some topological classification results. It doesn't show too much, but at the bottom of that slide, this is a result by Husken and Sinistrati, where they show that if you have something that is too convex, then in that case, actually all the singularities are the type of spheres and cylinders. So in particular, that tells you, or they can show that if you do surgery in this case, or if you continue the evolution, where you're gonna see is only handle bodies. So basically you have a classification of the type that you have in 2 dimensions, that if you have something that is orientable, everything is the genus, right? I mean, everything is classified by the genus of the surface. So they found a condition in higher dimensions using mean curvature flow. I mean, this was actually known, but they found a proof of this using mean curvature flow, that under some geometric conditions, all the objects are actually handle bodies. And there are other topological results that you can do using curvature flows. I chose these 2, but there are other examples. I wanted to finish, and I spoke a little bit faster than I thought. So I have like 7 minutes, I think. I wanted to finish telling you a few results that I have worked on, just so you know a bit of my background. On the case of curvature flows, this is not everything I have done, and I wanted to say maybe a few words about the last result, but I don't know if I'll have the time, and maybe I'll say a couple of words. So I chose 3 topics on the evolution of graphs. Everything that I have said so far about flows has been about compact evolution. So I've been talking about evolving manifolds or curves that are compact. If you go to the non-compact world, there are many other things that can happen. Many things are not as clear if you don't have compactness. And the simplest case of this is the evolution of graphical solutions. This was, so I'm assuming here that the evolution is going to look in this case, like in this parametrization, and in this case, the equation is given in this form. This was first studied by Ecker and Husken, and the first thing that you see when you look at a graphical mean curvature flow is that solutions tend to exist for all time and not have singularities, which is very different to the other case. So if you're looking at a graph that is entire, then the evolution is not going to have any singularity. And even more, if you know that is asymptotic to planes at infinity, then they can predict how the behavior at t equal infinity is gonna look like. As t goes to infinity, how this is gonna look like. This has applications also in terms of the compact case, because you can localize many of the estimates that you do in this case to obtain. So they use their work actually to obtain local estimates even for compact ones. But today I want to say a few words of things that I have done in the non-compact case. So one thing that I worked on many years ago with Oliver Schnurer, we wanted to see what happens if you do graphs instead of entire over a domain. One thing that we realize is that when you start with an initial condition that is a graph over a domain, think about a compact domain if you want, like the one that is in the background here, then your solution, you're going to find a solution that remains a graph, but your domain of definition is going to change. When you see that the domain of definition is changing, here we look at proper graphs only. You can think about other conditions, but in our case, there were things that we're just going to infinity at the boundary. Is that the domain of definition actually is something that is also evolving by mean curvature flow. So one possibility in something that you can do in this case, one possibility to study weak solutions is to study the evolution of the graph over an initial domain. And the domain that you see for every time is actually a weak evolution of mean curvature flow. So this gives you a definition, a weak definition of evolution of mean curvature flow in one dimension less. This is very similar to the idea that Husken Ilmanen, for instance, use in their work of inverse mean curvature flow. In their case, they extend by a certain particular kind of evolution in one more dimension, that is translators. But this can also be done in other cases and more generally. In fact, if you have, this is more maybe for experts, but if you have no fattening for your domain in the evolution, then these two definitions actually agree. The one that we find as the evolution of graphs, and the one that you find using the level set formulation. Okay, so something that I said here many times is that you can find a solution that does this or that or whatever. And one issue when you have evolutions that are non-compact, that is that in general, you don't know if you have uniqueness or not. Uniqueness is a difficult problem when you're talking about things that are not compact or without any other assumption. So the second work that I want to mention is work that I did with Toti Daskalopoulos, where we actually study the uniqueness of solutions. And in this case, I'm just stating the result when you have entire graphs. So the Eker-Husken solution is actually the unique solution. And this also works for the work that I just described under some conditions on the behavior at infinity, that evolution is actually unique. If you're radially symmetric in dimension 1 is also unique. And also if you have something that, if it's convex, is unique, but you can relax a little bit the convexity. And if you have that the second fundamental form is bounded from below, then you have actually the evolutions are unique. In general, they're not known to be unique. And one other thing that I'm not saying here, this is only in the class of graphs. So you may have, and actually not in Euclidean space, but in other ambient spaces, there are examples that show that you can start with something that is graphical, and you have the graphical solution, and you also have a solution that is non-graphical. So you actually have phenomena of non-uniqueness. They're not super easy to describe when they happen, but it can happen. And let me see the time. I'm gonna finish with this, so I'm not gonna talk about this. This is the last thing that I wanna mention. Also, when you want to study what we call type 2 singularities, so these fast occurring singularities that we expect not to happen, these are usually modeled after eternal solutions. And eternal solutions, the simplest case are solutions that evolve by translation. And so, yeah, I wanted to show you a classification result on that and some pictures. But since my time is up, I'm just gonna finish showing you two pictures, and we did some classification result on certain family of translating solutions. And I'm gonna stop here.
Thank you so much, Marielle.
Thank you.
Someone have questions to do? I would like to ask you, because I believe what happened if I have a homogeneous space working with mean curvature flow. You know about it? Because I try to find papers related to that, but I can't find a lot of papers. I am interested more in minimal submanifolds, and it is the case which happened in mean curvature flow with the minimal submanifolds is given by this, no? So are you working maybe with a homogeneous space, or is not, or
Yes.
also, yeah?
Yeah, I mean, yes, I have an answer for that. Actually, there are very few references, I would say, from that point of view. We have a recent paper where we look not exactly at this, but we look in the case of solved manifolds. Just in that case, of solutions that are emerging of subgroups, and even these are very different than in the Euclidean case. So there are some examples of translating solutions or self-similar solutions, I think, in the context that you're asking, but there are not many general results. I think people are just looking at examples and observing that they are quite different from the classical case,
Yeah.
let's say the Euclidean case. But I don't think there are many general results.
Yes. Okay. Okay. Thank you. Thank you so much. Thank you for your presentation, to accept also our invitation, and we would like to say that tomorrow we will continue
Yeah.
I
the
think
seminar.
Brian has a question. He has a
Sorry, Brian.
Me ibas dejando afuera.
Sorry. Okay.
Hello, Professor Mariel. Thank you for your talk. Very interesting. And more than a question, I want to say a comment that maybe for me it is not completely intuitive, the relation between the geometric flows that you define in terms of the differential structure of the manifold, and you from that you obtain topological properties. For me, that is not very intuitive, and with your talk, I think maybe I can understand. I could understand a little better why is that. So, well, it was a comment more than a question. So, thank you.
Thank you.
More questions to do? Sorry, Brian. No? Okay. Okay. Thank you. Thank you so much. We would like to say that tomorrow we will continue our conference workshop with Jason start, and we finish with Yutuka, Yuyushi Fukuoka. And we hope to all of you be tomorrow. So thank you so much for being here. And if you would like to say something, Brian, or Duban, no, it's okay. So thank you, and see you tomorrow. You can see the schedule in our page, and the time for Europe, Brazil, and Argentina. So see the page, and we hope to see you tomorrow. Thank you so much.
Thank you for the invitation.
Thank you, Maria. Bye bye.
Bye
Thank you.
bye.
Bye.
Bye bye, everyone.